A very warm and pleasant morning to our respected speakers, honorable dignitaries, delegates, and all dear participants. I welcome you all to today for the day 3 of the short-term course organized by the Department of Physics, NIT Srinagar. To start today's learning journey, we are being privileged by our respected speakers, Professor Rajendra Singh and Professor Aloke Kanjilal. We will be having two sessions for an hour each. We wish participants a very happy and knowledgeable experience. Now, starting with our fifth session for day 3, I would like to introduce our speaker, Professor Rajendra Singh. Professor Rajendra Singh is presently a professor at Department of Physics, IIT Delhi. His area of interest are gallium nitride-based materials and devices, gallium oxide-based devices, growth and characterization of semiconductor nanowires, wafer bonding and layer splitting of crystalline materials, 2D, 3D interface, 2D quantum materials and devices, CVD, MOCVD, and MBE growth of semiconductors and quantum materials, nanolithography and nanofabrication. He has made significant contribution in establishment of National Research Facility NRF at IIT Delhi. He has about 140 publications in international journals. He is a recipient of MRSI Medal Award for 2017. He also received a Teaching Excellence Award from IIT Delhi in 2018. Now, I would request Professor Rajendra Singh to kindly start with the session.
Yes. So, is it visible? My slides are visible?
Yes, sir. We can see the slides.
Okay. And I have to choose a pointer. Yes, a pointer. So my pointer is also visible, I think.
Yes, sir.
Okay, so good morning to all the participants of this short-term course on journey from semiconductor physics to smart devices to intelligent automation. So thanks for the kind introduction. And first of all, I would like to thank Dr. Shah for inviting me for this short-term course, and also, like, let us say, discussing with us regarding the organization of this short-term course in collaboration with the Semiconductor Society of India. So I am actually the secretary of Semiconductor Society of India, and we keep on organizing these kinds of very useful short-term courses, conferences, and so on. So it is actually within the, like, let us say, a mandate of our Semiconductor Society of India. So I'm thankful to Dr. Shah for collaborating and involving Semiconductor Society of India also in this short-term course organization. So as you see, I'm going to talk about a very, very important aspect of semiconductor materials and devices, that is the electrical properties. And in many cases, actually, like, let us say, when we try to find out the electrical properties of semiconductor materials, and also we try to characterize semiconductor devices, so we look into some analysis methods. And these are the, like, let us say, analysis techniques and methods which I am going to talk about today. And so what I am going to do is, this is actually outline of my talk. So as Dr. Shah told me that in this audience and participant, there are a number of students from masters also. So I have, that's why I am taking, like, let us say, it in the kind of tutorial mode also, and then later on showing some kind of, like, let us say, research results of my group, just salient research group results. So it's not that my entire talk is like, let us say, on our research what we are doing here in IIT Delhi. And in between, I will give some useful tips also, that when you are characterizing electrically the semiconductor materials and devices, what are the common mistakes which, like, let us say, sometimes experimentalists do, and how you can, like, let us say, get more reliable data and more reliable results, and its analysis also. So I will be talking about the resistivity and Hall measurements on semiconductor thin films, as well as in the bulk material. I hope I am clearly audible. That is not an issue. Is it okay for all of you?
Yes, sir. Yes, it is fine.
Okay, thank you. So I will be talking about the four probe technique, then the current voltage measurements on devices, And here I have chosen examples of two, like let us say, types of structures. One is the Schottky barrier diodes. In this area, my group also works quite, let us say, in an involved manner, and ohmic contacts, which is a very, very important kind of structure whenever we are trying to characterize a semiconductor material or device. And how to determine the barrier height, which are like, and the contact resistance using TLM method. I will be introducing you to this also, although some of you might be knowing, but maybe some master students might not have heard that much in detail. And in connection with this one, I will also show you some of the results on the nickel on GaN, so wide band gap semiconductor. I will be telling you about gallium nitride and the Schottky barrier diodes, which we fabricate on these materials. And also a new type of interface structure, that is graphene on GaN. So graphene, many of you have heard. So we have actually first time, sort of, not exactly first time in the world, but like let us say the initial studies which we started on graphene on GaN Schottky diode. So 2D material, 3D material, so 2D, 3D interface. And then lastly, I will be talking about the capacitance voltage measurements on Schottky diodes, and if the time permits, MOS capacitor. So in the semiconductor research area or even semiconductor industry, so a lot of these materials are characterized electrically, because for semiconductor, the electrical properties are very, very important. So these are characterized using these techniques like what I have shown you here: resistivity, Hall, current voltage, capacitance voltage, and the reliability of the devices and their properties, the interface between metals and semiconductors, between semiconductors and semiconductors. Electrically, they are characterized using these techniques which I have shown here. So before going to the talk, I would like to introduce briefly my research group at IIT Delhi. This is the Advanced Semiconductor Materials and Devices group. And here, primarily, we work on wide band gap semiconductors. So many of you have heard silicon. Okay, silicon is actually, sorry, the workhorse of semiconductor industry, because all our CMOS memories and microprocessors, they are made on silicon. But beyond silicon, we have compound semiconductor like gallium nitride, which is actually, after silicon, the second most important semiconductor material, gallium nitride. And its band gap is much higher than silicon. Silicon, we have 1.12 electron volt, but for gallium nitride, it is about 3.40 electron volt. So there is called the wide band gap semiconductor. We have recently, like let us say a few years back, a new material, ultra wide band gap material also has come into picture, and lot of research internationally is going on this one. This is called the gallium oxide. So we do a lot of work on gallium oxide, gallium nitride thin films, nanowires for their potential applications in electronic devices like Schottky barrier diodes, transistors, and optoelectronic devices like photodetectors or LEDs. And the group is also specialized on electrical transport properties of these materials, whether in the, like let us say, thin film material, bulk material, or the devices like Schottky diodes or high electron mobility transistors. So we have all the facilities to characterize Hall, resistivity, IV, CV, low frequency noise as a function of temperature also, starting from liquid nitrogen to room temperature and a little bit above that also. We also have a lot of research efforts going on in the direction of heterojunctions between 2D materials and inorganic semiconductors. You have come across now 2D materials is the buzzword and very, very hot and interesting topic worldwide. So graphene, MOS2, WS2, and gallium selenide. So there are like let us say number of 2D materials, and we have in the past few years we have started activity in the area of 2D 3D interface, like 2D material and the 3D material, normal 3D material like gallium nitride or even silicon also. So we study the 2D 3D heterojunctions, and also the effect of irradiation, because a lot of these devices, they work under harsh environments, specifically the wide band gap semiconductors. So we study the effect of gamma rays, the ion irradiation on the electrical properties and even the structural properties of these semiconductors. And a lot of work has been done in our group on the LGAN-GAN high electron mobility transistors, which are the transistors which will be used in 5G applications for high frequency, high power applications, and similarly on gallium oxide and MOS2. So these are actually some of the research activities which we are carrying out in our group at IIT Delhi. So with that, I will switch on to the, like, let us say, the topic which I'm going to. Hello?
Yeah, please, sir, carry on, sir. Please carry on, sir.
So
Rajendra
if there
Singh,
is question,
sir,
okay,
please.
thank you.
Please,
So
sir, carry on.
all of you know, so the resistivity of semiconductors, I'm starting from the basics. Okay, so for semiconductors, both electrons and holes are the carriers. So you have a semiconductor. In semiconductor, you have electron as well as semiconductor is possible. So here, the current density J is directly proportional to the electric field E. And the constant of proportionality is called the conductivity. And conductivity is given by this formula, where Q is the elementary charge and mu n plus mu p. And mu n is the electron mobility, n is the electron concentration. Similarly, mu p is the hole mobility and p is the hole concentration. So conductivity, it is given as sigma is equal to this one, and it is the inverse of resistivity. But we know that semiconductors are of two types, n-type semiconductor and p-type semiconductor. So from the law of mass action, which is Pn is equal to Ni square, so n, if it is an n-type semiconductor, then n will be very, very large in comparison to p. So this is actually for semiconductor, this is the property. So hole concentration will be much, much smaller than n. So in that case, this part can be neglected, and we arrive at a simpler formula where sigma is equal to rho, so rho is equal to 1 upon q mu n. So this is actually the formula for the resistivity. If it is a p-type semiconductor, then we will be having resistivity is equal to 1 upon q mu p. Or the conductivity is given by formula sigma is equal to q mu n. And now what happens is the resistivity, when I'm trying to measure and calculate for semiconductors, then I come across two types of samples. One is the bulk semiconductor substrate. All of you have heard about semiconductor wafer. Okay. So like in silicon, you can get 2-inch wafer and 4-inch wafer up to maybe like 12-inch wafers also. State of the art technology is 12-inch wafer, and even beyond that also is available. So what you do is, in our labs, we don't work with always large area wafers. We cut small pieces. And this is actually a bulk semiconductor substrate. Its thickness is a few hundreds of micron. Okay. So if you have 8-inch silicon wafer, its thickness is about 700 micron. If it is 6-inch, it will be 500 micron, and so on. These are international standards. So bulk substrates could be single crystalline or polycrystalline. So you have silicon, germanium, gallium arsenide, indium phosphide, silicon carbide, zinc oxide, many other, like let us say gallium oxide. So these bulk substrates are available in crystalline form as well as polycrystalline. So this is what I am looking at. I want to measure the resistivity of this bulk semiconductor substrate. We also have semiconductors in the thin film form, or what we call the, many cases, epitaxial form. Okay, so thin film is, this is an insulating substrate. Suppose this is the insulating substrate. On top of that, there is a semiconductor thin film which has been deposited, and its thickness can vary from a few nanometers to microns. So that is actually thin films. And these thin films you can have by silicon, germanium, any semiconductor you talk about, and could be single crystalline, it could be polycrystalline, it could be amorphous. So you see, from structural point of view, you have three possibilities. And then what you have is these thin films, their thickness can also vary, plus it can be of different materials. And then if you grow it on different substrate, it is heteroepitaxy, or let us say on a different substrate. Or if you grow a single crystalline thin film on a single crystalline substrate of the same type, then it is called homoepitaxy. And there are various methods to grow these thin films, and they have different applications depending upon their crystalline quality and so on. But main thing is that here the thin film, you are interested to measure the electrical property, electrical parameters of this thin film. Okay, not of the substrate. So that's why the substrate has to be insulating. So how to calculate? So resistivity, when we try to calculate of a semiconductor, there is a collinear 4-probe method, what we call. So in this case, what we do is in a lab, we cut a very small piece, typically 1 by 1 centimeter. Okay, this is what the kind of sample many of you get in your labs also. So not beyond that one. Okay, and there are 4 probes. Okay, they are arranged in a collinear fashion. So through the outer 2 probes, using a very precise current source, you pass the current, and through the across the 2 internal probes, you measure the voltage. So you have measured the voltage, and the current is flowing through the outer 2 probes. So in this way, actually, what is possible, that you are measuring only the resistance of the semiconductor and not the contact resistance. Otherwise, the contact resistance will also come into picture. So I will come to the contact resistance part a little bit later on. So once you have done this measurement, so your sheet resistance, what we call, is given by V by I. Okay, V by I is the sheet resistance, and resistivity is sheet resistance multiplied by the thickness of this substrate. So either this is substrate W or this is the thickness of the thin film. And the conventional unit of resistivity is ohm centimeter. Sometimes you can have sample in this shape also. So this is the diameter of the substrate. But this is rare actually. Mostly you get these kind of, let us say, substrates, which are actually square shape or rectangular shape. And now one important thing here I would like to mention, because these things maybe you have studied, but important thing is here is a correction factor. And I have plotted here this correction factor. This is actually on the x-axis, and d by s. D is the dimension of this substrate, which is 1 centimeter, and s is the distance between the 2 probes. So depending upon the ratio of d by s, the correction factor changes. So correction factor is, you can see here, starts from 1, and then it keeps on increasing, and then it saturates up to 4.3 or something like that. So if you have d by s of 10, so something, if you have a probe distance 1 millimeter and you have d 10 centimeter or 1 centimeter, then you have d by s of 10. So you are here actually. So you see the correction factor is huge. It is more than 4. So in the calculation of sheet resistance, you should not forget this correction factor. Otherwise, your resistivity or resistance, and hence the resistivity, will be at error by a factor of 4. So this is huge actually. So that's why experimentally, when you are measuring using this collinear 4-probe method, you have to be careful about this correction factor. So this is one important point. Now, the resistivity versus dopant concentration, as you see, in single, I have just given one example, but this is quite universal behavior for all the single crystalline semiconductor materials. Why I have given it? So that you can appreciate how much could be the resistivity change, but that's why we call them semiconductors. Okay, so if you see on the y-axis, it is 10 to the power minus 4 ohm centimeter. This is for single crystalline silicon, and at the highest is 10 to the power 3, which is more insulating. So you have resistivity varying from semi-metallic to the insulating regime. And how it happens? By changing the dopant concentration. Okay, so this is actually, so by changing the dopant concentration, either P or N, you can tune the resistivity in this order of magnitude, 7 orders of magnitude. You can make it metallic in nature, or you can make it insulating. And this is the range which is more like semiconducting range, I will call 10 to the power minus 1, 1, 10, or 100. So this is something like, let us say, these are the resistivities where semiconductor materials find a lot of application for the devices. And this curve is at 300 Kelvin. So for all the other semiconductors also, like gallium arsenide, gallium nitride, or even like, let us say, gallium oxide, this is the kind of universal behavior you will see in those semiconductors also. So now I come to the Hall effect in semiconductors. All of you have studied Hall effect. How to apply it to semiconductors experimentally. Okay, theory you know, I am just summarizing in front of you, but I assume that the Hall effect you understand. And in Hall effect, what we do is, so this is just only the schematic. Okay, so just try to appreciate that this is only the schematic which we study in the books. So what you have is, along the X direction, there is a current which is passing through the semiconductor material, along the Z direction, you have applied a magnetic field, and then along the Y direction, perpendicular to both X and Z, you measure the Hall field. And how this Hall field develops is due to the Lorentz force, which is like, let us say, which acts on these carriers. So either it could be holes or it could be electrons. So if these are holes, they will turn in this direction. So this will be like, let us say, positive potential. And if these are electrons, then this phase will become at, like, let us say, relatively at negative potential. And this is what you measure using a very precise voltmeter. You can measure the Hall voltage. So this is the Hall voltage, and Hall voltage divided by W is the Hall field. And this is actually the current density. Jx is equal to QVxP, and the Lorentz force is balanced by the Hall field, and you see the balance of the forces at equilibrium. And you can actually, like, let us say, make a little bit, like, let us say, substitutions and arrive at the value of Hall voltage. So the important thing here is in this relation, if you see the Hall voltage, so you see Hall voltage you can measure. This is what you are measuring experimentally. You are applying a fixed magnetic field that you know already. You are passing an electric current that also you can measure using an ammeter. So this is known, experimentally measured. Jx you know, Bz you know, and the thickness of the substrate you already know of your initial substrate, either it is thin film or substrate. So from that you can calculate the carrier concentration. If it is hole, then you can, if it is p-type semiconductor, you will be able to measure the hole concentration. So here actually we talk about a factor Vh is equal to Rh and these Jx, Bz, W, where Rh is called the Hall coefficient. Actually you measure the Hall voltage and from there you calculate the Hall factor. So Hall factor actually is related to the P and N. So it is minus for N-type carriers, electrons, plus for this thing, for the holes. So you see Hall measurements in conjunction with the resistivity. What it gives you, lot of important things. It gives you, because you see Hall measurement, you measure the carrier concentration. With the resistivity method, you have calculated the resistivity. Now resistivity is dependent upon the carrier concentration and the mobility. So you know the resistivity, you know the carrier concentration, so you can calculate the mobility also. So if you do resistivity and Hall measurements in semiconductors, you can find out three very important parameters of a semiconductor material. One is resistivity, second is the carrier concentration, N-type or P-type, that also you can distinguish the type of the carriers, and the third thing is the mobility of the carriers. So here again a word of caution that if we go a little bit more into the detail, then the Hall coefficient is actually given by Rh is equal to small rh. So what is this small rh? So this is actually a Hall factor which is dependent on the type of scattering. Now in semiconductors, what happens is there are different scattering mechanism, but the main mechanisms are phonon scattering or the lattice scattering and the impurity scattering, ionized impurity scattering. So if in a semiconductor you know that it is the phonon scattering which is dominant, then this RH factor is 1.18. So if you are not using correctly this factor, then you are already 18% actually error is there in your calculation. If it is ionized impurity scattering, this factor is 1.93. So you are almost 93% error in your calculation for the carrier concentration. So if there is an error in the carrier concentration, also you will be having an error in the mobility. So that's why you have to be careful when you are doing this measurement to properly, like let us say, consider this Hall scattering factor small rh. So this actually what I showed you was the schematic. Now I come to actually how it looks like. So there are various Hall measurement geometries. Okay, it is not so simple that you make contacts and you get the results. What you have to do is you have to put your sample into proper shape. And this is actually one of the shapes what we call the Hall bar geometry. So this is actually Hall bar geometry is like I will say the most precise geometry for semiconductor thin films. Okay. And here what you see is that you make actually, so what I am doing here is there is a thin film. Okay, there is a substrate below and we have etched out this kind of thin film structure on the substrate. And then we are taking these contacts very like precisely. And how you can ask, like, let us say how we can do that. So that you do with the help of sophisticated photolithography and etching techniques. So that is the limitation. That's why in the labs, normal labs, we don't use Hall bar geometry, which is more preferable, because the photolithography and the etching, so this is actually, let us say, in many cases not available. Otherwise, this is the most precise geometry for the measurement of sample geometry for the measurement of Hall effect. And here I am showing you the, like, let us say, the microscopic image, how it looks like, and zoom view. You see, this is how is the structure. So these are the bigger contacts, and this is the thin film blue, and these are how the and these yellow, like, let us say, are showing the contacts. Yellow areas are showing the contacts to this semiconductor, and all these contacts have to be very good ohmic contacts. Otherwise, your measurement will not be that much precise. So that is actually the Hall bar geometry. But in our labs, most of the times, what we do is we take other configuration. So these are actually other contact geometries I am showing you. These are all possible. And this is actually the generalization of that one, arbitrarily shaped sample. What this is called, actually, I think most of you know, this is the van der Pauw technique. Many of you might be knowing the van der Pauw technique for the measurement of resistivity and Hall. So what I will say is, if you don't have sophisticated lithography and etching techniques available in your lab, you adopt actually this kind of simpler geometry, what is we call the van der Pauw geometry. And here the advantage is that you can actually, like, let us say, you are a little bit flexible in putting your ohmic contacts, and your sample shape can also be a little bit arbitrary. So that is what actually, you need the flexibility in normal lab conditions. So what you do here is you make 4 contacts, as I have shown you earlier. So 1, 2, 3, 4. So first what you do is you pass the current through 1, 2 and measure the voltage across 3, 4. Then you switch. Then what you do is you pass the current through 2, 3 and measure the voltage across 1 and 4. And what you can do is you can reverse the current direction, then measure the voltage and takes its magnitude. And you can do, actually, let us say, more switchings also. You can take, like, let us say, not RA, RB, you can do 2 more configurations. And then the average of that one. So what is the sheet resistance in this van der Pauw geometry is RS is equal to pi by ln2. ln2 is the natural log of 2, and RA plus RB by 2. So you take the average of RA and RB and multiply it by pi by ln2. This gives you the sheet resistance. And what is the resistivity? Resistivity is the multiplied by the thickness. So this is how you get the sheet resistance or the resistivity using the van der Pauw technique. Now in the Hall bar Hall measurements using the van der Pauw technique. Okay, you do the cross actually. Earlier what you were doing is you were passing the current through one side and measuring the voltage across the other 2 edges. Here what you do is you pass the current diagonally through the 2 diagonal contacts and measure the voltage across the 2 diagonal contacts. And then what you do is you measure the VH in that case. This is the voltage. If you have a perfect symmetric, then this voltage, like, let us say, when you are not applying any magnetic field. So here you are applying magnetic field. Without magnetic field, it should be 0. Otherwise, you will be having the voltage which is induced. That is called the Hall voltage. And using this formula, which I have earlier also shown you, IB, I is the current, you know the magnetic field, Hall voltage you have measured, you can calculate the sheet concentration. And now you know the carrier concentration by thickness, you know the resistivity, you can measure the mobility of the carriers. So you see, this is now, let us say, what you have learned from resistivity and Hall effect measurements. You can measure the carrier concentration, the type of the carrier, the mobility of the carriers, and also the resistivity of the semiconductor material or thin film or the substrate. Now what extra we can do? Just these 2 techniques, what extra information I can get? Okay, what extra information about the semiconductor? So what you can do is, if you have the option and facility to do temperature dependent measurements. So let us see what it can do. I will just show you graphically. So these 2 measurements You either can do in collinear four-probe method or van der Pol geometry or precise Hallbar geometry. What you do is you measure the carrier concentration as a function of temperature. Okay, you have a cryostat and you load your sample there and do the same measurements as a function of temperature. Now plot it, the electron concentration as a function of the reciprocal of temperature. What you are going to get? You are going to get this kind of graph. Okay, so this is the graph. So what you see here is there are three regimes actually in this graph. One we call the intrinsic range or regime. But second is the saturation range. Third one is the freeze out range. This is the kind of graph you will get. And again, I want to emphasize here, this is a very universal graph. Not only for silicon, but the same kind of graph, similar kind of graph, you will get for all the semiconductors when you will do temperature dependent carrier concentration measurements. Okay, here we have just given an example of silicon where dopant concentration or carrier concentration at room temperature is 10 to the power 15. So we know from semiconductor that Pn is equal to NCNV exponential minus Eg by Kt is equal to Ni square. This is the standard formula. P is the hole concentration, N is the electron concentration in the same piece of silicon, same sample of semiconductor. Nc and Nv, the effective density of states in the conduction and valence band respectively. And this is the Eg. And this is Ni square. Okay, so first thing, what you do here is, if this intrinsic regime you fit, you see it is a line. Okay, electron density versus 1 by T. So it is actually a straight line. If you fit it, what you can calculate is the band gap of the semiconductor. You see, you can calculate the band gap also of the semiconductor using same measurements. The technique is the same, resistivity and Hall effect, but you have to do temperature dependent. What else I can measure? So from the saturation range, you can find out the carrier concentration that we have already done also. But there is a third regime, which is called the freeze out range. So in this freeze out range, what has happened? The donors or acceptors, they are partially ionized. They are not 100% ionized. So what will happen is, as the temperature will increase, they will start becoming more and more ionized, or the ionization efficiency of the donors or acceptors will increase. And at this edge of the saturation regime, it will be 100% ionized. So from this slope, so now if you fit this line, you can also get the ionization energy of the donors or acceptors, or what we also sometimes call the activation energy. So you can also get the ionization. So you see, now you have found out so many things about a semiconductor. You have found out resistivity, you have found out mobility, carrier concentration, type of the carrier, its band gap, and the ionization energy. So using the electrical measurements, you have found out so many things about the property of the semiconductors. Now I come to the ohmic contacts to semiconductor. Okay, so you see, if there is a device in a semiconductor, what happens? Whenever there is a junction, what we mean by junction? Junction means there are two different, like let us say, regions in a semiconductor, and there is a potential barrier which is existing at some interface. So it means there is a potential barrier, and this potential barrier will give rise to some non-linearity in the IV characteristics. So this is what we call actually the rectification, non-linearity in the IV characteristic. So it is given by this barrier which is actually existing at the interface, whether it is a PN junction, whether it is a heterojunction, whether it is a metal semiconductor junction. But what we need is, I also want to put my current inside this semiconductor device and take it out without disturbing. At, like let us say, when I am putting in and taking out, at those points, it actually should not disturb the device behavior. Means these contacts should be linear. And these are actually specific types of metal semiconductor contacts, what we call the ohmic contacts. If you deposit any metal over a semiconductor, you will find there is a potential barrier. It is non-linear. But we, using some specific processes, techniques, we try to make it ohmic. So as the name indicates, in the ohmic contact, it is a special metal semiconductor contact where there is a linear and symmetric IV characteristics. And it also has negligible junction resistance. relative to the total resistance. So in this way, what will happen is it will not disturb the action of the active device. Active device means PN junction or transistor. It will not disturb the behavior of the active device. I want to see the behavior of the PN junction. So you need actually one contact from the P side, another contact, ohmic contact from the N side. And these are in no way disturbing the behavior of the PN junction or the PN interface. I hope you have understood about the ohmic contacts, and it should have good adhesion technologically and should have good thermal stability, and the voltage drop across an ohmic contact should be negligible. It's the same thing. Okay, or I can say it's contact resistance. So the most important property is the contact resistance should be very small. So there is a very, very important figure of merit for ohmic contacts. What we define is called the specific contact resistance. Now remember it actually, because many of you might be doing research in semiconductor materials, devices. So there is a very important property, what we call the specific contact resistance, RC dash. And what it is the reciprocal of del J by del V at V is equal to 0. So what you have is you plot the IV characteristics or JV characteristic, take its slope, and its reciprocal is the specific contact resistance. Remember, this is current density, and this you have to take at V is equal to 0, and its unit is ohm centimeter square. Now another important thing which I give you about RC dash is that for like let us say if you want to define what is a good ohmic contact and what is not so good ohmic contact, how do you say that? So first thing is by, like let us say your IV characteristic. If it is linear and symmetric, okay, in the first and the third quadrant it should be symmetric. So linear and symmetric, that is one thing. But what about, like let us say, its specific contact resistance? So if it is close to 10 to the power minus 1, minus 2, you will say it's a relatively, like let us say, good ohmic contact. If it is lower than that one, 10 to the power minus 3, minus 4, it's very good. And if you are touching this 10 to the power minus 6 ohm centimeter square, then it is like, let us say, excellent ohmic contact. And in state of the art devices, whatever you use actually in silicon based devices or gallium nitride based devices or gallium arsenide based devices, you try to achieve actually in the industry, semiconductor industry, or even research also, research labs, 10 to the power minus 6 ohm centimeter square. Then only you say that my ohmic contact is of, like let us say, the best quality. And here I show you, I'm not going into actually, because metal semiconductor contacts, there is a complete, like let us say, theory for the current transport process in metal semiconductor interfaces. And what we define is actually this RC dash. I'm just giving you straight away the relation. So this is actually dependent either on the barrier height or the dopant concentration through this formula. Okay, again, I will not go into the detail, but I can just tell you this is from the thermionic emission model and this is from the field emission model of metal semiconductor devices. So this graph actually summarizes everything what you need actually for the fabrication of a very good contact resistance or ohmic contact. So you can see it is actually 10 to the power minus 6 to 10 to the power 6. So these examples are given for platinum on silicon, aluminum on silicon. So you can say if you reduce actually the barrier height between metal and semiconductor 0.85, 0.6, 0.4, you drastically reduce actually the specific contact. So what you have to keep in mind when you are fabricating a metal semiconductor contact, your barrier height should be very low. Second thing is if you do heavy doping. So then if you do very heavy doping, then you don't, even if you have, let us say 0.6, you can go down to very small values of, like let us say, specific contact resistance. So while fabricating ohmic contact, from physics point of view, what you have to keep in mind, the metal that you are choosing, it should have low barrier height, and the semiconductor layer which you are having beneath this metal contact should be heavily doped, and then you can get a very good ohmic contact. And now this is actually the transmission line model which I am coming to for measurement of the ohmic contact. So I have given you the figure of parameter, how to quantify. You see, that is actually very, very important. But how to measure it experimentally? So the experimental measurement is done using this transmission line model. Here what is shown is, this is the semiconductor piece. Okay, so I am making two contacts here. I want to measure actually the contact resistance here. So if you see here, there is a resistance. If I apply a battery, I pass the current and measure the voltage, I can measure actually the resistance. But I will be measuring the resistance across these two terminals. And this total resistance includes the resistance of the metal, which of course is very small, resistance of this interface, and the resistance of the semiconductor. So this total resistance is RT is equal to 2Rm plus 2Rc plus semiconductor resistance. But in most of the cases, the metal, because their carrier concentration is very, very high, so they are actually, like, let us say, not putting much resistance, or their resistance is much smaller in comparison to the RC. So we put this as RT is equal to 2RC plus R semiconductor. And now using photolithography, again here we have to resort to lithography and etching. So what you do is you make these kind of metal contacts. So all of these, so this is actually the semiconductor below, which I am showing you. And on top of that, you put a series of these contact pads. So these contact pads are having, like, let us say, this width W and their length is L. And then we are having successive pads with gaps D1, D2, D3, D4, and so on. So this D1, D2, this keeps on increasing. And W and L is kept constant. Okay, so this is what is a series of contact pads. So I want whatever contact material I want to characterize, I will put it in this shape using lithography and etching. And now in this geometry, again, I have depicted this thing. It's the same thing which I have shown in my earlier schematic. RT is equal to 2RC plus R semi. What now I will do is, I will measure this RT as a function of D1. Okay, this total resistance I am measuring as a function of D1, D2, D3. So it is something like this one. I measure between these two contact pads. I measure my RT between this one and this one, and then so on, so that I can make a complete, like, let us say, graph like this one. So RT as a function of D, which is D1, I have taken points D1, D2, D3, D4, D5, these are discrete points. And now I fit it. When I fit it, this is the equation I already have. RT is equal to 2RC plus R semi. So 2RC plus this, I can put it in this shape or in this form. R sheet is the sheet resistance, and D by W. So D is actually this in the on the x-axis, which is a gap between the contact pads, and W I have already shown you. This is the width of this contact pad. So by fitting this line, what I will get is, you can see, by fitting, I plot RT versus W. If I fit it, I will get the value of R sheet by W. W I already know, so I can calculate the value of R sheet. And resistivity is sheet resistance multiplied by the thickness of the film. Here I am using small d as the thickness of the film. And the specific contact resistance, because I am more interested, this anyhow I can calculate from the other methods also. I am more interested in specific contact resistance. So this RC dash is equal to RC. This RC is the contact resistance, and it is given by the intercept on the RT axis. Okay, intercept on the y axis is 2RC. So its half is RC, and W and L multiplied by W and L. So these are already I know, because I have made these contacts by myself. So these geometry I know, their dimensions I know. So RC now I have got. So RC multiplied by W multiplied by L gives me the specific contact resistance. So this is actually the method for measurement of, experimental measurement of the specific contact resistance. So the last, like, let us say, Dr. Shah, how many minutes I have now? Because accordingly I will go.
Sir, you can take 5 minutes more, sir. Then we'll have a discussion.
Okay, okay.
Sir, you can take 5 minutes.
Okay, I will cut down some
5 minutes, sir. Yeah.
Okay, so
then we'll have a discussion, sir. Then we'll have a discussion.
Current voltage measurements on Schottky diodes. I just come to this part. Okay.
Okay.
So you have three types of basic devices: Schottky diode, PN junction, MOS. As I have told you in between, that always there is a barrier. Okay, this barrier actually gives the non-linearity in the IV characteristics. So, and there are different types of current transports in the Schottky barrier diodes. So Schottky barrier diode is a metal semiconductor contact, but there are, like, let us say, ideal Schottky barrier diodes, and there is non-ideal Schottky diode. What do we mean by that? So if we apply a voltage forward bias, then the current can flow either using thermionic emission, means this process one, electrons getting energy thermionically and going over the barrier. You can also have quantum mechanical tunneling, where it doesn't need to go over the barrier. If it is thin, it can tunnel through. And then you have recombinations in the space charge region and in the neutral region. Here the ideal diode, the IV equation is this one, very famous, all of you know, I is equal to Is exponential QE by KT minus 1. But in practical diodes, what we have to do is we have to modulate it in this form, I is equal to Is exponential QE by NKT minus 1, where N is the ideality factor. So you see how close we are to the ideal behavior in a Schottky barrier diode is defined by this ideality factor. It is a very, very important parameter of a Schottky barrier diode. So for relatively, like, let us say, good diodes, it should be less than 2. So now another important parameter of a Schottky barrier diode is the barrier height. So one is the ideality factor, which I can calculate from the IV measurements. Another one is the height. And we have two models, theoretical models. One we call the Schottky Mott model, which was given in 1930s by Walter Schottky and Sir Neville Mott. So it is given by the difference between the work function of the metal and the semiconductor electron affinity. So this is from the energy band diagram. You see, this is the barrier height. So it is proportional to the metal work function. If semiconductor is fixed, as you increase the metal work function, it should increase. But what about the practical Schottky diodes? So there was actually the interface model given by Bardeen, Sir Johann Bardeen, you know, he got the Nobel Prize also, two Nobel Prizes. So he actually proposed that there is an interface which contains interface states. So first time the surface state idea in semiconductor devices was given by Sir Johann Bardeen. So what he told is there are interface states, and these interface states will actually lock the Fermi level. This effect is called Fermi level pinning. And if the Fermi level pinning happens, so this Fermi level will not be able to shift as per the metal work function. And then in that case, it will be given by this formula. SBH is equal to, is the difference of the EG, the band gap, minus the phi naught. What is phi naught? It is the charge neutrality level. So this is a special state at the interface. So in this interface, if Fermi level is locked to this particular state, then it is electrically neutral. The surface or the interface is electrically neutral. Otherwise, this surface will be having, or interface will be having, some charges. So in this case, you see, it doesn't depend upon the metal. So in one case, it linearly depends upon the metal work function. In this case, it doesn't depend at all. So what we have is, when we fabricate in our laboratories Schottky diodes practically, I will show you an example, that we always get barrier height in between. Okay, so upper limit is Schottky Mott model, lower limit is Bardeen model. So that physics wise, I know when I am trying to make a Schottky barrier diode, where it should lie. And I just give you one practical example from the work of my earlier student, Dr. Ashutosh Kumar, who is now working in Sweden. And he fabricated this nickel on GaN. So you see, this is a gallium nitride thin film, about a few micron on sapphire, which is insulating. And these are actually 2 bars. So you see, this is actually titanium, aluminium, nickel, gold. And it is deposited by E-beam evaporation, and there is a rapid thermal annealing at 850 degree for 1 minute. So this is a very precise recipe. If you go here and there beyond these process steps, you will not get a very good ohmic contact. And after that, these circular dots of Schottky diodes of nickel were deposited, and now you can see the IV characteristics. You see, this is actually rectification. Very nice rectifying behavior is shown. And when I'm plotting it in the semi-log plot, so what you can see is there is a linear regime, actually this one. Okay, here now, this is the inset, linear, and this is log linear. So this linear, like let us say regime, you fit. And when you fit it using these equations, so this is the same equation I have used. So you can also, like, let us say, get it, the slope is equal to Q by 2.3 NKT. So you can experimentally, you can measure the slope. So you can experimentally calculate the ideality factor. And also from the intercept, its intercept on the y-axis, you can get the IS value, the reverse saturation current, and the reverse saturation current, you can calculate the barrier height. So you see, we have got a barrier height of 0.9 electron volt, which is a really good value, and identity factor of 1.3, which is also like, let us, pretty good value for gallium nitride based Schottky barrier diodes. So you see these nitrides, what we have chosen, 3 nitrides, what we call, you can have gallium nitride. This is a family of wide band gap semiconductors, aluminum nitride, indium nitride, and when we can tune the band gap from 0.6 electron volt to 6 electron volt. And they have number of applications starting from white LEDs. All these LEDs which you are using in your homes are based on gallium nitride. That is actually one of the biggest applications. Then high frequency applications coming in 5G. So like for the discovery of these LEDs and lasers, the Nobel Prize in Physics was given in 2014 to Professor Akasaki, Professor Amano, and Professor Nakamura from Japan. And this is actually, like, let us say, the another kind of diode which we have fabricated, which is a very novel actually. It's a very new work. Graphene. All of you know about graphene. It is a 2D material. It's very thin. So we could transfer actually thin, like small samples of graphene on n-GaN. Okay, so these are actually some Raman measurements we have done. I will not go into the detail due to shortage of time. So this graphene on gallium nitride. So this is contacting the gallium nitride. So this is a graphene on gallium nitride Schottky diode. So you may assume like how like should be graphene is having a metallic behavior in principle. So you see this current voltage characteristics. This is for the nickel GaN, which I earlier showed you, and this is for the graphene on GaN. So graphene on GaN also can give you a very high quality Schottky barrier diode. And here we have using our fittings, this thermionic emission theory, which I have told you. So for graphene on GaN, we have got 1.3 identity factor and 0.6 electron volt, the barrier height. So this is actually first kind of report showing the Schottky barrier diode, that you can fabricate very high quality Schottky barrier diode using 2D material on a 3D material. And okay, anyhow, we tried to explain actually the Fermi level shift in graphene due to its interaction with gallium nitride going up, then is for the pristine. So because this is actually, let us say, the electronic band structure of graphene, and you can tune the Fermi level in this graphene and make it n-type or p-type also, just by making it in contact with the metal or in making it in contact with the gallium nitride. This was very, like, let us say, good work which was done by my student. So I will now try to stop here. Just 2 minutes I require. So you see, Schottky barrier diodes, you can do CV measurements. So in CV, what you do is you measure the capacitance. Instead of IV, in the reverse bias, there is no DC current which flows. So you measure the capacitance. It acts like a parallel plate capacitor. And then what you do is you plot CV and you take 1 by C square. So 1 by C square, it is actually, if you take this one, it is inversely proportional to ND. And it gives you a straight line. So if you fit this straight line, from this fitting of this straight line, it is connected to the ND. So experimentally, you can measure the dopant concentration and also the barrier height. So from this intercept. So you can calculate using CV measurement the carrier concentration in the semiconductor as well as the barrier height inside the Schottky barrier diode. And these are the typical, like, let us say, devices which we use, like Keithley's SCS 4200 parameter. So it has actually inbuilt program for IV and CV. And we have this probe station using which, like, let us say, you can go from room temperature to 200 degrees Celsius, and it has probe tips. You put the sample here, and you can, like, let us say, contact to even very small contact pads also, not millimeter. I am talking about 10 micrometer, 20 micrometer, which have been defined by lithography. So here I will stop. I will not go into the capacitance measurements of MIS or MOS capacitors. I think maybe some other time. So thanks for your attention. And I am actually currently in physics as well as a joint faculty in electrical engineering. And you can also see our current publications in my Google Scholar page. So thank you all.
Thank you, sir. Thank you very much.
Professor Rajendra.
Yes, please.
Thank you, sir. Thank you. Thank you, sir. Thank you very much, sir. Thank you. I mentioned your name and your organization also, Semiconductor Society of India, in my inaugural speech.
Yeah. Yes. Thanks for that.
And to Sharma
Yes.
Saab, I made a thing. Thank you very much, sir, for readily agreeing in this joint venture, which has been very successful. Almost 300 students are participating every day. Almost.
Yes. Yeah. Very nice. Very good
And then
initiative from
also,
your
I
side.
have requested, I have also requested Sharma Saab regarding the chapter of semiconductor physics in Jammu and Kashmir also.
Yeah. Definitely. We will. I think we shall work for that one. And
Yeah,
like let us
please.
say, we can. I think we have one of our student here, in your department, Dr. Zubair is there. I don't know whether today he is attending or
Zubair
not.
Sir,
Saab is
we
there,
have
sir. Zubair Saab is there. Zubair Saab
He's
is here.
here.
yes, sir.
Okay.
Yes, sir. He's here.
Yeah.
He's
So
also connected. He was supposed to join us. He was supposed to join us and
okay.
make a thank you.
So he's
Yeah,
our
we can.
student from
Yeah,
IIT Delhi. Yeah.
yeah. So you are in the
Yeah,
same
hello.
center, in the Khare Saab center?
Yes, sir.
In the Khare
Actually,
Saab?
like
Dear
this.
student, just give me the
Yeah.
few
This
minutes. Okay.
nanoscale research facility. Yes.
Okay. Nanoscale research facility.
Yeah.
Then also
It
we
has
have also one good
Yeah, please.
yeah, one good initiative we are holding it after every 2 years. Nanotechnology for better living. It initiated from
Okay.
IIT Kanpur, then it went to IIT Kharagpur. This year, Khare Saab said that we will also join you.
Okay, that will be great. Yes, we will do
Yeah,
that.
yeah, please. I'll send a mail to you, sir. So we are
Okay.
the tentative schedule is in the month of September, from 7th to
Uh-huh.
11th of September. From 7th to 11th of
Yes.
September.
Sir, there are a
We'll
few
see all these
questions.
possibilities. I'll request Zubair Sahib to make a lead in this in these two initiatives. One is a chapter in semiconductors in Jammu and Kashmir. The other one
Yes.
is regarding the joint organization of nanotechnology for better living.
Yes. So Zubair can take
So
the lead actually, and he can serve as a
yeah,
connecting link between IIT Delhi and NIT Srinagar.
yes,
Ah,
sir,
Zubair
yes,
is
sir.
here. Muhammad Zubair is
Yeah,
here.
hello,
Yes.
sir.
Yeah.
हाँ
Very good morning
हेलो
to
सर
sir. Like,
कैसे हो
Zubair.
जुबेर कैसे
yeah, sir,
हाँ
I'm fine, sir. मैं बहुत अच्छा हूँ, sir.
हाँ
Actually, मैं आपसे
वेरी
start
गुड
में, but
ओके
this lecture is start, so I cannot talk with you. So your
यार
अपना
lecture
लेक्चर
is
दीदार
बात
कराइए
करेंगे
जुबेर साहब, अपना अपना स्टाफ, अपना वीडियो जो है ऑन रखिए, अपना दीदार भी कराइए, राजेंद्र साहब भी।
नहीं
definitely,
हम
sir.
भी अपना दीदार करवा देते हैं
सर
वैसे मैंने
प्लीज, सर
सोचा कि
प्लीज,
वो
Yeah, okay.
एक्चुअली आई एम नॉट इन ए वेरी गुड सेटिंग बट स्टिल आजकल
ना,
और कोई
इट्स
ऑप्शन
ऑलराइट
नहीं
सर। एक टीचर की सेटिंग क्या होती है सर? टीचर इज ए सिंपलीफाइड। एक टीचर की सेटिंग क्या
Yeah,
होती है?
definitely.
तो ये ब्यूरोक्रेट्स की सेटिंग वेटिंग होती है, बाकी
यस
लोगों की
यस
होती है।
बात सही कही आपने बात सही कही बिल्कुल
सर हम लोगों को इन चीजों के क्या, हमारे जो है बच्चे हैं, दे गेट बेनिफिटेड, सो
यस
वी आर सेटेड वी आर मैं कहता हूं कि हमें तसल्ली मिलती है दिल को जब हमारे बच्चों को फायदा मिलता है।
जी, बिल्कुल, sir.
तो जुबेर आप इसमें थोड़ा लीड लीजिए जो हमारा आईआईटी दिल्ली का एनआरएफ है और एनआईटी में भी कुछ फैसिलिटीज के लिए एंड वी विल आल्सो हेल्प यू आउट एंड डॉक्टर शाह हैं ही इज सो एंथुसियास्टिक सो सपोर्टिव सो टेक दैट एडवांटेज एक्चुअली ओके और आपको कुछ भी
Yeah,
यहाँ
definitely,
मिलेगा
sir. In the last month of in the last week of March, Professor Neeraj Khare was visit NIT Srinagar. So
ओके
he
ओके
also discussed about this NRF facility.
ओके
So वो
ओके
सर हम सब करा है हुआ है. So definitely we will benefit it for this NIT Srinagar with the NRF
यस यस
in future.
ओके या
Regarding
एंड वी
Singh
हैव
Saab, so we will go to our business. The normal
यस
business is the discussion.
यस प्लीज प्लीज
Then in the first slide you said, sir, now you are doing the work on collaborating or joining the three-dimensional materials with the graphene.
यस
That makes the material multifunctional.
Yes,
You have a
true.
semiconducting properties, you have a dielectric properties, you have many more properties. That's agreed. Sir, is there any mismatch between the two? Mismatch of rates rather.
Yes. So you see, this is actually like, let us say, mismatch is always there, but this is a different kind of interface. It is actually a van der Waals interface. So it is not purely covalent interface. So that's why we don't, like, let us say, need to worry too much about the lattice mismatch. Okay, that is the one thing.
Okay.
And since it is very, very thin, so as you are talking about the functionality, so the functionality is that, so this graphene can work as a metal, but it can also let pass through the light, because if you have metal, so if you put a metal, it will not let the light pass through it. So if you want to do photo
Yes.
detection, it will not be actually so good for the photo detection. But if you have a graphene, it is conducting as well as transparent. So, and moreover, it is also giving you the barrier. So using this barrier, you can separate out the electrons and holes, and that will give you a very good photo responsivity. So that was
Good.
actually the first idea with which my student, he started doing this research actually. And we actually, like, let us say, started working on this topic. So that is one thing which actually we focused on. And now we are also going towards the semiconductor heterojunction. So this was a metal semiconductor, like MOS2 is a semiconductor. So MOS2 on GaN or MOS2 on silicon. So there is one of my students is there, Sahin Sarifi. He is currently working on gallium selenide and silicon heterojunctions. So this is actually a 2D material and 3D material interface. So it's also giving us very good, like, let us say, rectification properties. And we are trying to understand the properties of this heterojunction. So here the possibilities are, like, let us say, a number of possibilities can arise if you can combine these two 2D materials and 3D materials.
Good. Good, sir. Thank you, sir. Niklesh, go ahead.
Okay, sir.
Take questions from the chat box.
Sir,
Go ahead.
there are a few questions from the participants. First is from Nikita. If we use the contact other than ohmic contacts, then what are the major parameters of semiconductor which gets affected?
So you see, all these parameters, as I have shown you in my slides, you will not be able to calculate. Suppose you are measuring the resistivity. So you will not be able to measure the resistivity accurately, because you see, we are relying on the fact V by I. When I am measuring sheet resistance, I am saying R sheet is equal to V by I. But if it is a non-linear contact, then it depends upon which voltage. Okay, so V by I will also keep on changing for the same material. So we will never be able to find out the accurate value of the sheet resistance. And if you don't find sheet resistance, then you will not find good, like, accurate value of the resistivity. So similarly for devices, this is for the material. For the devices, it will alter the, like, let us say, the behavior of the device. You want to find out the PN junction characteristics. But if you have a contact which is non-ohmic, then your PN junction characteristics will not be revealed properly. So then you will fit these IV characteristics, try to find out the built-in potential for the PN junction, you will find inaccurate values. So it is very, very important actually. This is what I say, because I am working in semiconductors. So I know you should use, actually, if you want to find out very accurately the properties of your semiconductor material, specifically semiconductor material, should always try to make a very good ohmic contact. That is the starting point.
Thank you, sir.
Thank you.
Yeah,
Next one.
Niklesh, there is my one question. Sir, you are talking about the specific contact resistance. So how we can get the low value of this specific contact resistance?
Yeah, that's what I summarized actually in one of the slides. I gave you two things. One thing is the barrier height should be low. So you should choose a metal.
Okay.
When you deposit it over the semiconductor, the barrier height should be low as possible. That is the one criteria. Second thing is, you should try to make tunnel contacts. Tunnel contacts, how you can make? You can induce a very thin region below this metal, which is very, very heavily doped. And if it is heavily doped, then the electron carriers will tunnel through it. So this is actually, like, let us say, gives you very small value of the ohmic contact resistance or the contact resistance. So two things: low barrier height and
Barrier height.
tunnel contact or tunnel contact between the metal and the semiconductor. So that is why when I was showing you my gallium nitride work, I showed you 4-layer contact: titanium, aluminum, nickel, gold. And then you have to do annealing. So there is a complete process you have to develop for making a very good ohmic contact. It's not that any metal you deposit on a semiconductor, even if it is a low barrier height, it will be a very good ohmic contact resistance. So in semiconductor technology, ohmic contact resistance or ohmic contact, making a very good ohmic contact is a very, like, let us say, a kind of patented technology.
Okay, sir.
Okay, sir.
Okay, sir. Thank you,
Next
sir.
one.
Thank you, sir. Sir, next question is from Shraddha Mahakal. Can we use this method for isotropic and anisotropic materials too? The 4-probe method, sir, she is referring to.
Yeah, but then you have, okay, you see, okay, it's a good question. I think what she is asking is more like, let us say, materials which are anisotropic. So it can be used for that also, but you have to take care of, like, let us say, in which direction your contacts are. Then you have to, like here, when I'm talking about silicon or gallium nitride, so this is at the surface what we are making the contacts. So it usually doesn't matter in which direction we are making. But if they are, like, let us say, anisotropic materials, many of these ferroelectric materials are anisotropic, or piezoelectric materials, then you have to keep in mind in which direction. So when you are doing lithography, so that's why in those cases lithography is very, very important, because then you can precisely align your contacts along some particular direction. Then you are measuring the resistance along that direction. Okay, and then you make the contact along the other direction, maybe perpendicular, and then you are measuring the resistance or resistivity along that direction. So that you have to know initially, like how your sample is oriented, and accordingly you have to precisely put your contacts using photolithography.
Okay, sir. Sir, next question is from...
Thank you, sir. Niklesh,
Yes, sir.
we are moving, we are running short of time. It's already 5 minutes late. Kanjilal also might have joined.
Yes,
So I'll thank Professor Singh again. And then
Thank you,
I wish
Professor.
Professor Singh in person someday to Kashmir soon.
Definitely. Yes.
So, but don't forget to come along with family.
Yes.
Professor Singh, I wish
Yeah.
you in person along with family.
Okay, thank you
Please,
very much. Yes,
please do
yes.
join us in September. Hopefully,
Yes,
we'll do
yes.
it in. That's a hybrid conference that is online as well as offline.
Okay.
So we wish you to be here. We wish you to be here, sir, in the month of September.
Okay.
Thank you, sir.
Yes.
Thank you.
You.
Thank you. Nicholas,
Okay,
please
thank
invite
you.
Okay,
Kanjilal.
sir.
Thank you. Thank you.
Tanzila.
Thank you.
Yeah, okay, now starting
Professor
with our
Kanjilal.
sixth. Now starting with our sixth session for day 3, I would like to introduce our next speaker, Professor Aloke Kanjilal. Professor Aloke Kanjilal is a professor of the Department of Physics at Srinagar University and an expert in material science, material processing and characterization. He has made a fundamental contribution in various fields, including radiation dosimetry to photocatalysis. He received extensive experience in thin film growth and modification of materials under extreme environment. He is recipient of prestigious Alexander von Humboldt Fellowship. He recently received Research Excellence Award from Shiv Nadar University. He published more than 100 articles in reputed international journals and conference proceeding on novel experimental results and ideas of processing and characterization of materials and devices.
Can you listen to me?
I would request Professor Aloke Kanjilal to kindly start with his session.
Yes, Professor Alok, sir.
Can you listen to me?
Yes, sir. Yes, sir.
Sir.
Hello.
Hello.
Yeah,
Professor Kanjilal.
You are audible, sir.
yes. So I
Hello,
just
sir.
want to
Morning.
say,
Good morning. Good morning.
morning.
Welcome.
Welcome.
Welcome,
Okay,
sir.
thank you very much.
Welcome.
So I was really
Welcome.
late to
Please share
join
your slides,
because
sir.
I had morning class actually just finished and then I joined here.
Okay. Okay.
So,
Okay.
so let me
Okay,
share
sir.
the slide.
Okay. Please, sir. Please do.
Your content. Can you see the slide?
Yes, sir. Yes, we can see the slides.
Very good. So I go to the full from now. Also to minimize this one. So let me see. Okay. So I am Dr. Aloke Kanjilal. I'm a professor in the Department of Physics, Srinagar University. So I am really grateful to the Professor M.S. Shah and also the organizer for inviting me in this short-term course on journey from semiconductor physics to smart devices to intelligence automation. Okay. So this is my email ID. If anybody would like to contact me in future, so you can also contact me in this number. So before I start with, I just, because what I experiencing every day in the class is that there are some kind of problem. I just make myself invisible so that it will be easy for me, because it is making something disturbing here. Okay. So if you don't mind. Hello.
Sure, sir.
Yes, sir. Yes, sir. Please, sir.
Yes, I'm trying to. Okay, it's gone now. Okay, so now, so here actually I'm going to give some kind of explanation. So what actually I'm trying, that it is not only that to show that what I'm doing, but rather I should give some kind of idea that what people has to think about to pick up any subject to go for research. Okay, so so there are many different steps. So, and if I'm not so wrong, then if you see that if you go to any class, even many faculties are here, so you can see that many times I found that people having very limited concept before telling anything for future applications. Okay, so that's why I thought that first I give some kind of initial idea that what is actually semiconductors, how they are, means how the bands are formed, why the band gap is there, and then ultimately I'm connecting with the low dimensional structure formation and then utility of that structures for future applications. So this is the way actually I'm proceeding. Okay. So here you know that semiconductor is the kind of material which is lying in between the two different edges, that is the conductor and the insulator. So here you can see in the right hand side why it is not going. Okay, I can put it down. Okay, so what you can see that here in the metal you do not have any band gap, so the bands are actually overlap. So that's why you say that in Fermi level, this is called Fermi level, or the dotted line you can see over here. So where you can get the density of state, that means that your electron will be populated up to the Fermi level. So, but in case of semiconductor, you have a gap. The dotted line is not completely enriched with the electrons, but in case of insulator, the gap is really so big that you have a far difference from the Fermi level, so that it means that there's a long distance between your Fermi level to the valence band maximum, where your maximum electron can stay. So to reach this kind of concept, so first you have to know that. So what are the elements actually in the periodic table can behave like a semiconductor? So this is a complete periodic table. You can see that out of this periodic table, you can see I am just focusing on a certain region, which are very, very important in understanding the semiconductor physics. So here, out of these different materials, you can show over. We are showing over here. So you can see this these metals, the silicon and germanium, they are called the elemental semiconductor. That means that they are inherently semiconductor. They have a little band gap all the time is present. But not only this, whenever you can add some extra material, and that means that you are making some compound semiconductor. Then here actually simple example is that if I mix carbon with silicon or germanium, then also we can also use, or we can prepare a new type of semiconductor. So my just before that actually when Professor Singh was showing, so he was using gallium nitride, gallium. So it is all compounds, how they are realized, why they are giving like semiconducting property. So those things actually need to be very clear. So another set of semiconductor you can think is that the gallium nitride, what he already told in the previous lecture. So here also you have seen that we have the set of elements, that the aluminium, gallium, indium. When they are making compound with the phosphorus, nitrogen, even the arsenic, antimony, they can create a compound semiconductor. That means that here two different elements they are joining. They are making bonds to create a different types of semiconductors, so compound semiconductors. They are not elemental anymore. Similarly, we can also go forward. We can think of 2,6 semiconductor, where you are taking care of the elements, the cations from this, not so the elements from the 2B and the 6A, when they are making some bonds, and they can also create the new type of 2,6 semiconductor. So we are using different semiconductors having different band gap, different connectivity. So all these things actually we have to take care of whenever you think of any future applications. Okay. So recently, you know that there are 2D materials that are very challenging nowadays, and a lot of people actually focusing on that, where actually people just considering the 6A and the 6B material when they are making the compounds, they are making the transition metals like dichalcogenides, that is in short term is called TMDC semiconductors. So generally, people are mostly focusing on the 2D form, so because the 2D structure can give the semiconducting nature. So we are not going in details about this 2D, but better I initially say that how these bonds actually form, how the semiconducting nature is coming, what is the structure required for think of different applications. So I'll take you the application part because my research is focusing over there. But since I see that many of the cases when people join after MSc, so they have very limited understanding how these materials actually forming. So that's why I just give a very short overview about that. Whoever joining, I expect that some MSc students also in this school, so they can all get some kind of information. They can enrich their knowledge before making thinking of any particular research in future. So whether it is semiconductor based or it is the semiconductor metal based, or like what Professor Singh was saying that Schottky junction, the metal semiconductor junction. So whatever you think of, but you have to have a very clear idea that what these materials and how these materials can give and what is the property of these materials actually has. So semiconductor materials, generally, you know that we always use this solid material. Even it is 2D form, but they are all solids. Okay. So whenever you are talking about solid, that means that you are not talking about a single atom. You are talking about some atomic distribution. That means that you are dealing with a many body problem. That means where you have a certain number of atoms are involved in making the dimension. Even it is small, low dimensional to the bulk, whatever it is, but you should have a certain number of atoms should be involved to make the structure. So generally, you know that for silicon, we have about 5 10 to the 20 order of numbers of atoms per centimeter cube existing. So it is not a silly joke to control such a large number of atoms in such a small volume. So that's why we need to have a very clear idea that how these bonds has formed and how ultimately can clear the bands. So if you, before going to the many body problem, we just think about what is called silicon atom. So if you see the electronic structure, so since by knowing the number of electrons in the outer orbitals, you can distribute in different orbitals, like the 1s, 2s, 2s2, 2p6, 3s2, and 3p2. In this way, you can distribute. You can see that we are classifying two different parts. One is called the core electrons, that is the 1s, 2s, because they are screened by the valence electrons, which is made of the third level, that's the 3s2 and 3p2. But these levels are whenever the atoms are in an independent form. But these atoms, whenever they are making the bonds, so then they should be in the excited state and they are hybridized. And when they are making the hybridization, then the S, because since you have one electron free here, so there is one empty space is there, so electron can be shared from S to P orbital, so that they can be hybridized, and these 4 electrons now can share between the different atoms to create the bonding, so that they can make it's called the covalent bonding. So they can share the electrons so that they can fulfill their number of remaining electrons, whatever you have. So here actually, since you have in the hybridized state, if one electron can provide 4 different electrons, 4 different states, then the other silicon, which are making the bonds, they can also share the other 4 electrons, so that ultimately it can complete the number of electrons 8 to fulfill the remaining electrons. So this is the way you can get the stability. So silicon making a kind of network, the one actually it is shown over here. So now, if I go to the again once again to that small section of this periodic table, then you can see that if we can take out gallium and arsenic, so whenever you are making the gallium arsenic compound semiconductor, then you can see that gallium atom having the valence electron 3, and the arsenic it has 5 electrons. So when they are making the bonds, that means that they are asymmetric in nature. You can see that. But ultimately, in total, they are making the electrons, 8 electrons already fulfilled. But thing is that because of this little difference in the number of electrons in the valence band, so they are having some little polarization. So how to find that this is really polarized? Though it is covalent bond is forming, but still it is polarized. But that we can easily measure by knowing the electronegativity. So whenever you see the electronegativity chart in the periodic table, and if you can follow the electronegativity numbers, then you can see that whenever I'm taking this gallium and arsenic, in total, whenever the compound actually form, you have to consider both 1.6 and 2 together to get the what is the total number, that is 2, because it is, if I say that one is giving electron, one is receiving electrons, in this way, if you can add them up, then 2 minus 1.6, well, total is 4. 1.6 minus 2, that's 0.4 is you can get. So yeah, in a periodic table, if any compound actually formed, and if the total electronegativity is lying in the range of 1.7 to 4, then we call it as ionic solid. Like sodium chloride, if you take the sodium and the chlorine, you can find the total electronegativity will be lying in between the 1.7 to 4.0. So that's why sodium chloride behaves like an ionic crystal. In this case, like gallium arsenide, if you see that if I take the 1.6 minus 2, then even 2. Because you can get a positive term, the 2 minus 1.6, in total it is 0.4. So this 0.4 is lying between the 0.3 and 1.7. That's why it's called the polar valence state. But whenever you are taking silicon bonding, then both having the 1.8. If you subtract between the two different electronegativity, then 1.8 minus 1.8 equal to 0. So since it is lying within the 0.0 to 0.3, then that's why it's non-polar. That means the silicon in this case is a non-polar covalent state. But in case of gallium arsenide, still it is semiconductor, but it will be behaving like a polar covalent semiconductor. So this is the way we can classify different semiconductors. Okay, but now the problem is that till now we know that how the bonds are formed and how the compounds are making different semiconductors. But now what will happen that when many different atoms now are how close these atoms can come close? Because you are saying that gallium arsenide compound is forming, but how close they can come? So this we can easily understand by knowing the interatomic potential. So I think that many of you already learned previously that Lennard-Jones potential. So here actually I'm writing a very general form of this potential, where R is the distance between two different atoms. So one is the first part actually is talking about your repulsive part, and the second one is the attractive part. So whenever you have this, you consider both the component together, and where M would be more than N, and R is the distance, interatomic distance, then you can get the potential distribution with respect to the R. It is something like you can see the repulsive part actually is dotted line, dashed line, and the lower part actually is showing the attractive line. So when you put them together, it will give you a kind of overall tendency. So now you can see that it is the minimum distance it can come where actually the potential will be minimum. That is a stable state, you know that. But now if you know the potential, you can easily find out how much force actually is there. So force can be determined by, you can take the derivation of this. So if I take the derivation of this with respect to the R, then you can get where you can get the 0. So here the force will be the minimum point, the force will be 0. But if you go to the right hand side of this minimum, then you can get the attractive force. But if you go below that, then the electrons will be repulsive, then the atoms, they repel each other. So they do not allow the atoms to come much closer beyond this F equal to 0. So F equal to 0 is the force, where the force are balanced, so that is a stable state. Okay. So this is the way actually things are formed. And this is completely controlled by the Pauli exclusion principle, because you know that when in quantum mechanical, if you think that two electron cloud actually come close, your atom means electron clouds are there at the end. So when they are overlapping, then once the two electrons cannot take the same state unless they are not having the two opposite spin. Okay, so based on this ideology, then the electron cannot go to the two electrons of the same spin cannot take the same state. So this is the other idea to what is called why it is called repulsive in nature. Now, how to realize that what is how this kind of phenomena can give us about the band distribution, or how these bands actually form. So let's consider two hydrogen atoms. So I think that in the book actually, if you go there, you can see that it starts with the hydrogen atom because it has only one electron. because whenever we are dealing with the many body problem, then you always consider at least one electron in the valence state, so that our life will be much easier to handle it. Because if you take more electrons, then it need the computational help to solve the problem. So basically, we are solving the Schrodinger equation. Okay. So here actually for simplicity, we take hydrogen atom where we have only one electron in the outer orbital, which make the bonds, okay, to get the hydrogen molecules. So if Ra and Rb are their nuclear equation, and then R and the distance between the two different nucleus is called R, then we can write the Hamiltonian. Okay, so that is written by its kinetic energy part for two different atoms, and they are interatomic atomic interaction. That is a Coulomb interaction between the electron and nucleus interaction. So all components has been taken care of. You can see that the R1 and R2 is the electronic distribution. This is the R2 minus R2. This small R1 and R2 are the position of the electrons in the two different atoms. So, so in this way, actually, they are making the total Hamiltonian can be realized. So I go a little fast. So if anybody having any problem, at the end I will discuss about this. Okay. So as I said that since we have the Pauli exclusive principle already applied over here, we cannot write simply that two atomic wave function, the two particle wave function can be written in terms of the multiplication of two different potential. Okay, like this we cannot write. So in that case, you know that since electrons, they are fermions, okay, half spin is there. So then total function, wave function, because you know that whenever you are dealing with the Schrodinger equation, you ultimately deal with your solution. That is the wave function you are dealing with, and this and whenever you solve it, then ultimately it will be asymmetric in nature. Okay, because if you exchange it, the particle will be exchanged. Because they are equal shape they are ideal in nature, but they are indistinguishable. So that's why the exchange probability will be also considered into taken into account. Now, if we can neglect this atomic and the electronic interaction, so then we can solve this problem by total wave function can be determined. And there are two different parts we can easily determine. One is the spatial part, one is the spin part. Okay. So now, whenever we are writing there are two different possibilities for getting the asymmetry, either consider the spin or either consider the spatial part. So by taking both the condition, we can write in the beginning, we can say that it is a spin asymmetry. So when the spins are opposite in nature, then the total wave function can be written is a proportional to the wave function will be is a addition of two different components. One is the phi a phi b and plus here the R1 and R2 will be exchanged. Okay, the position, because they are exchangeable, so because they are indistinguishable, that's why they can take any positions there. So in this way, if I do not take the consideration of the asymmetry in the spin part, take the consideration of the asymmetry in the spin part without considering the spatial part, then we can get the single state. In this case, what will happen? The total spin, they will be cancel each other, and total spin will be 0. Okay, so in singlet state, your total spin will be 0. Now, in the other case, we can think of when the asymmetry is coming in the spatial distribution. That means that if the position will be different, the negative part is coming. You can see the negative is coming over here, but spins are symmetrical. They are all aligned in the same directions. The total spin, then in that case, if I add them together, then minus half, 2 minus half will be added. Then it will give you the 1. That means total spin will be 1. And this kind of state will be called as triplet state. So many times you can see that in the molecular, people use the molecules and find out different states, the single states, triplet state. You should know that what is called triplet state, where the spin is 1. So where the symmetry is, when the symmetry is maintaining the spin direction, but the spatially they are asymmetric in nature. Similarly, if I do a single state, the asymmetry in the spin, not in the spatial distribution. Okay. So now, whenever we are thinking about the psi both parallel, that means that it is an asymmetric triplet state we consider. So if we consider that both electrons are the same position, that is R1 equal to R2. So in some way that both electrons are taking the same location. What will happen in this case? Then we can understand that on the second one, so this part will be going to be 0. So that is not possible. That means that it is impossible to get simultaneous occupation of the two parallel electrons to take place to take the same state. So this leads to a depletion of the electrons. That means the electron will be depleted from there, and that is called as anti-bonding state. Okay, so many times actually people don't understand what is the meaning of this and what is the meaning of that. But in case of the electrons, whenever they are having an opposite spin, and that means that in this case the electron can be at the same place, so can get the same state because they have the opposite spin, which leads to the accumulation of the electrons between the nuclei, and that is called the bonding state. Okay, so that means that we can say in one way that when two atoms now make the bonds, okay, or they are just coming close to each other and make this compound, then we can write the total expression in terms of the two electron wave function. That is called psi r1 r2. Because since it's a quantum mechanical nature, so you do not know the indistinguishable the electrons, so that's why you can write in the both different forms. So in the wave nature, so if we write the symmetric and the asymmetric, then you can see that in this case, when two electrons, the nucleus are sitting at the center of this peak, so if they are coming close, and in this case, when they are making a bond, so in the bonding state, the electrons, both electrons are opposite in spin, then they can, spatially, they can come closer, and so that means electron can make a cloud there. So, and in the probability, if you take the probability, then you can get the psi squared. So in the opposite case, then in antibonding state, and in between, since they are the spins are same, but spatially they are opposite, they are cancelling. So that's why in the middle, the electrons will be depleted. So no electrons will be existing between the two different nuclei. So you can also find out the energy levels. So if, the expectation value also can be determined by taking this molecular energy levels. And in this way, we can find out the two different electronic levels, the singular state and triplet state, and where E naught is the ground state when the atoms are not making any bonds. They are independent in the ground state. So in this way, we can make two different kinds of bonding. So sigma, when you have the s orbital, they are spherical in nature, and p orbital, they have the lobes. Okay, the electron distribution having some, it is not making a spherical symmetry around the nucleus. So in case of sigma, you can see that we can get the bonding and anti-bonding state. The anti-bonding, you say that the electrons are depleted from the middle of the two different electrons, but because of these, you have some kind of electronic distribution. So some kind of small dipoles may be formed. But here actually, when electrons are in the bonding state, the electron, they can occupy the middle part, the middle of the two different atoms. In case of px, p orbital, there are two, the px, py, pz, the three different orbitals there. So then, if we say the px, they are making the your sigma bonding. Then the other two bonds, so those are parallel, perpendicular in nature. Then you can get the pi bonding there. So in pi bond, they are the polarity is the opposite. So in this case, if you have the lobes, the plus and minus, then the other one will be opposite of this. So by considering this, we can think of py and pz. So in this way, pi can be getting the pi bonding and pi antibonding state. So when we are making a large number of electrons, we are considering, like in case of silicon also, we have seen that since we are dealing with the s orbital and p orbital together, then when I take all valence band together, then definitely you have to consider both s orbital and the p orbital together to make your electronic distribution according to the levels, energy levels you have. So now, because I just keep, because I just give the concept and then I skip over here so that if anybody have any doubt, I can discuss later on. What happens if a more number of electrons now, atoms now come into picture? So now, till now, actually, we are dealing with the two different atoms, like where actually you can think of the bonding and anti-bonding state actually formed. Bonding is the lower one, and the anti-bonding is the upper one, because high energy. So now, if I go to the molecules, then the molecule means two atoms having some distance will be maintained. So this is the A is the distance, the separation between the two different atoms. So in that way, actually, you can, if I consider the molecule as mode of two different atoms, like a H2O or something like that, then you can think, or if you have a more number of atoms also, then combination of all different electrons based on the different distances. Because if I bring the other atoms, like if I make the gallium, maybe I can say the sodium chloride. So if I bring the chlorine closer, so what will happen? The interaction will be different, level will be different. So because of that, actually, your dispersion of this triplet and the singlet will be different. And the tendency of the dispersion of this singlet and the triplet, the one actually it is shown in like two different lines for single atom, atomic levels. In the molecular level, it will be it will show kind of tendency of changing the changing their orientation. So so you can see kind of that kind of structure may be obtained. So now if you have many different atoms now combined, so you are making kind of cluster of n different atoms. Like I said, that we can deal with, we can just consider that one electron is shared from every atom. Then every different atom will contribute one electron to make this kind of bonding. Then what will happen? Every single atom will be corresponding, making their own singleton triplet state, and they overlap and making a kind of sequence of different levels will be formed. So if the number of atoms are really increasing in number, so you can see that here in this case the states are discrete in nature. But if you have large number of atoms, like a bulk material, whenever you have large number of atoms are involved, then it's a quasi-continuum state. Then you have large number of every atom, because though it is not logical to think about only one electron is shared by every atom, but for simplicity of our discussion, if you think of n electrons, actually n number of atoms are contributing n electrons, then n by 2 levels can be occupied, because you know that according to the Pauli's exclusion principle, every state can 2 electrons of the opposite electrons. And since the ground level, the bonding state is the stable state, then n by 2 levels will be occupied, and other n by 2 will be unoccupied levels. So that's why by showing different colors, the deep color actually shows that it's a occupied state, and the light gray color says the states are available but no electrons. Okay, so that's why it's called the quasi-continuum state. That means that if you can bring the atoms closer and closer, so attacking is more denser, then in that case your bands will be bending in that way. But if some atoms are there where actually the bands they can overlap, but at a certain distance, like at a distance a naught, you can see that the bands they bend in such a way that the continuum bands they have in between there is a gap. So if the gap is formed, then this kind of material is called as either semiconductor or insulator, depending on how much the gap is. Okay. So like here actually, so this is the basic concept of starting the why does valence band and the conduction band minima actually can be think of from this kind of this kind of definitions. So how to find out that whether it's a metallic or semi-metallic similar in nature? So you can see that here is the semi-continuum state. So if we give the temperature, then electron can go to the free electron part, the free space where the states are available. So they can conduct, and then they can scatter also. In that way, if you increase the temperature, then scattering will be increased. Then you know the resistivity increases. So for conductor, for like a metal, the distribution of the resistivity versus temperature is always increasing. But in case of semiconductor, since there's a band gap, then since you have the free space here, but you have the electrons much in this up to the valence band maxima, so you have to populate this conduction band so that this can participate in the conduction mechanism. So that means that with temperature, if you can give extra energy, because there is a KT, you are supplying the energy. If the KT is sufficient enough that electron can populate the conduction band, then they can participate, they can populate the conduction band, and they can, a number of electrons, it can reach to the conduction band, they can also participate in the conduction mechanism. So that means that in this case, in semiconductor, so if you give the extra electrons, so by giving the heat from external heat, then in that case, what will happen? It can make the conduction may happen. So the resistivity will be decreasing. So opposite tendency will be there. So it is the if you have a clear understanding of the band gap, how they are forming by overlapping of this your bonding and antibonding state of different atoms, then you can really understand that why the semiconductor actually with temperature the conductive resistivity decreases, and in case of metal it is increasing in nature. But the other thing is that when you are talking about a solid, the solid can be of different forms because they can be ordered, they can be polycrystalline in nature because some grains are formed, those are ordered, but not in totally it is ordered. So they can get the polycrystalline in nature, or maybe they are completely random in nature, like amorphous in nature. So we can get different types of. So like whenever you think of any band structure, so you have to have some kind of orderedness so that you can find out the brilliant zone and you can go for the band diagram. Okay, so for that actually we consider the ordered structure like the left hand side picture. So it's a small section actually I'm showing. That's called the unit cell. So it's the minimum cell, like minimum unit volume area you can think of. That's called a primitive cell, and this cell can be a simple cubic because in 3D it can be a simple cubic, because here in 2D actually it is showing like a square, but in 3D it will be cube. So it's a simple cubic. But if you have extra atom presence at the center of this kind of box, then it's called the body center cubic. But if you have the extra atom at the faces of this cubic unit cell, then it is called the face center cubic, FCC structure. We have also used this diamond structure because silicon is basically taking the diamond structure where you have the additional 4 atoms. Those are taking the positions here, and you can make different because it's a FCC structure, but you have additional 4 atoms which are taking the 8 different corners, middle of the corners. Now, in case of gallium antimonide or zinc selenide structure, they are making the zinc blende structure where the position of the silicon, where earlier actually it is occupied by the silicon, it will be occupied by the additional atom, that is the sulfur. So maybe if you can occupy by the sulfur, then the rest of the part will be taken by your zinc. So this kind of structure, because though looks exactly like a diamond structure, but since they are having different atoms, so it's called a zinc blende structure. So if you think of a very simple structure like FCC structure, so you can see that in this FCC structure, it is not the minimum volume actually you can occupy. You can further think of a much smaller volume within the FCC unit cell, like this way. Actually, the one actually it is shown over here. This small unit box within this conventional unit cell is called a primitive cell. Okay, so whenever you take the primitive cell, and you know that whenever you are exposing any metal to any X-ray to get the diffraction pattern, we are seeing the in the Fourier space. So that's why we have to think of the reciprocal space. That's called the Fourier space. So that is the picture actually is right hand side showed about the reciprocal lattice distribution of this FCC structure, and the lattice vector of this can be easily determined by knowing the your real component of this AJ and AK, and J and K can be 1, 2, and 3. You can replace that. Is if I find the B1, then in this case A1 plus A3 will be considered. Sorry, A2 and A3 will be considered. And here, this is the volume part. The volume conventional cell will be considered. So A1 plus A2 dot A3 will be considered. So that means the denominator will give you the volume of the conventional volume of this in the real space. And then if you know the corresponding vectors and the two different edges, then you can find out the corresponding unit vector in the reciprocal space. And what you can see that it is 2 pi by the L, which is in denominator. That means that it is not in centimeter in watts. So then generally we usually use this kind of concept for conserving. So by knowing this, also we can think of the cell layer. Like here actually I show some good example that this is the high resolution TEM images actually I have taken from some paper. What actually it is shown that whenever the aluminum arsenic or gallium arsenic, they are so that they are not making that much of strain. The lattice is almost close to the gallium arsenic. So it is by taking the heterostructure, by putting the aluminum arsenic and the gallium arsenic once again. So by sandwiching this aluminum arsenic, there is no difference except the atoms will be different. Your molecule different atoms will be placed instead of the gallium. You are just placing by aluminum, but it has different applications. But if there is it is not matching structure, then definitely germanium having from the lattice constant, silicon 5.43. So there are 4% mismatch. So that's why you can create some kind of dislocations at the interface. But here actually you do not expect the dislocations because they are lattice matched. Now this is a kind of chart that which shows the different types of semiconductors available and different lattice constant actually, because you know that for making this particular layer, the lattice constant, knowing about the lattice constant is very important. So lattice constant is determined from this interatomic potential distribution curve. I showed that where the force will be 0, the minimum of this curve. So in that way, you can see that silicon having a 5.4 angstrom, whatever your indium phosphide, it is 5.8, and if you go further in carbon right, it is even beyond 6.5 angstrom level. But how the band structure? Because whenever you are exposing this kind of materials to any photons, then you can see that they are absorbing at different wavelengths in different way. The absorption coefficient is not same. So because they are different, because that signifies that your bands are not flat in nature. They have some distribution. They have some deviation below this, because there are some minimum, there's some maximum in the valence band. So whenever you are really plotting the valence band structure by knowing the billion zone, then you can see that how the bands are distributed. So generally we showed by a straight line, by a conduction band and valence band like this way, but it is not like that. They have a kind of undulation and they're changing at different location. And here, by knowing the billion zone, you can find the different high symmetry points. The gamma is the center, and then if you go to the X direction or the L direction, that's the corner or the middle of the edge, then you can see that the electronic population will be different. The states will be different. So they are varying. And one more thing you can find over here, this is the two different cases actually, silicon and gallium arsenide actually compared. So silicon, the band, the condenser minima and the valence maximum, they are not staying in the same place. That's why they are indirect band gap. But in case of gallium arsenide, since the condenser minima and the valence maxima, they are lying on the gamma point. So that's why they are called as direct band semiconductor. So here you can see that in both the cases, in valence band, two different labels actually, which are connecting at the point valence maxima. And only the thing is that the slopes are different, and these slopes can be is very important factor. It actually helps us to understand that the effective mass of the because since we are talking about the holes, the electrons are populated up here, and whenever you are ejecting one electron to populate the conduction band, you are creating holes in the. So then we can find out the whether this hole will be heavy or light, depends on what the curvature would be, because the curvature ultimately determines whether it will be heavy hole or light hole. So since in this case you can see that it will be heavy hole because the slopes will be very low, but if the slopes are really high, then it will be light hole. So by knowing the slope, you can find out what will be your effective mass would be. Now low dimensional structure. So till now, whatever I said, it is the bulk. So then why the low dimensional structure is important? So first of all, it is already known to you because it is by now by attending some conferences, you already know that by reducing the size, okay, so you can play with the band gaps. That means that here actually kind of simulation of work, actually I collected from some paper, actually it says that how it is distributing. If I reduce the band gap, you reduce the distance between or reduce the size of this cluster, the atomic distribution will be different, and that's why your band gap will be also changing. So that means that even the silicon, the one actually I showed over here is the indirect band gap. By reducing the size, actually this silicon band gap can make is you can make a direct band gap semiconductor also, and that's why it can also emit light in the visible range. And using that, actually LEDs actually prepared. There are lots of papers where actually they are demonstrated that silicon nanocrystals can emit light in the visible range. So that means that what we learned here is that by reducing the size, your band gap actually opens. But how? So for knowing that, so this is one part. I'll come back to this point. Another thing actually is one thing on I should tell about here, that by reducing the size, we can also play with the surface area. Surface to your volume ratio also can be changed. So like here, actually, to see that I have taken a very small unit volume, 111 unit. I do not put the unit here. It can be centimeter, it can be nanometer, whatever you consider. So if I say that 1 unit of every different edges, the total volume would be 1, and surface area would be 6, because there are 6 different surfaces. So every surface having the 1 square. So then 6 into 1 into 1 square is the 6. But volume wise it is 1. So if I take the surface to volume ratio, then ultimately it is giving you the number 6. But if I take if I add 9 of such the cube, when 3 at different ages, each ages, if I consider the surface area will be 6 into 9, that will be, and if I consider those and take the surface area by volume ratio, then it will give me 2. Okay, if I start increasing the number of these unit cells joining each other and make this bigger volume of this, like a ball structure you are making, so 5 of different y direction, x direction, all 3 directions having the 5 units, then you can see that surface area now 6 into 25 and volume will be 125. If I take the ratio, it will be 1.2. So what I can see here, if I increase the volume, then your surface to volume ratio is actually going to decrease. So that is the advantage. That's why we are whenever it is not only the band gap we are dealing with. At the same time, whenever the surface area is actually important for some application, in that case, so you have to reduce the dimension of this structure. So here actually you can see that here indium gallium arsenic quantum dots fabricated on gallium arsenic. So is a so where the dots actually form a small structure which is sandwiched between the two different gallium arsenic spacers. So that means that what we learn from here is the increasing surface to volume ratio by decreasing the size of the structure. But at the same time, we should also remember that whenever we are thinking of any structure, we do have some kind of vacancies because some atoms may be not present there at the right in the periodicity. Then if you are missing some atoms in the order, then it can create the vacancy. And whenever vacancies are created, then you have the dangers that some kind of dangling bonds can be formed, and they can participate also in the conduction mechanism, and you can also find some different nature in your electrical property. So by using this property, the increasing surface to volume ratio, recently actually we published an article where actually we created the titanium dioxide nanotubes by electrochemical process. You can see that we create some nanotubes. So nanotubes are shown over here. So so these nanotubes also making some rim-like structures. Okay, it is not simple nanotube. The rims are there. So and we have heated in different temperature, and we found at certain temperature, generally because titanium oxide having three different phases. So out of these two different that is anatase and the rutile structure, they having the band gap of 3.0 and 3.2, and both the band structure can be observed in the UV's technique. And whenever we take the UV visible spectroscopy, we can see both the edges. That means that we can get a kind of junction between the two different structures. And utilizing this, actually, we showed that this increasing surface to volume ratio, and by utilizing these two different phases, we can increase the dye degradation possibility. That is the photochemical activity is increasing. Okay, so I'm not going details about this. So if somebody interested, then you can also read this paper. Also, we showed that by making the silicon pyramids by electrochemical process, you know that whenever we're making silicon solar cells, the most of the light actually reflecting back. Mostly 30%, 40% light is going backward direction. So they are non-utilized. So to utilize those things, so you have to increase the surface so the maximum light can be absorbed. So for that reason, actually, we showed that how the structure can be formed. We prepare some kind of pyramidal structure. And you know that whenever you are making a silicon solar cell, you have to coat some kind of anti-reflection coating. So here we consider azo layer, the contacting layer. At the same time, it will be also can give like a your anti-reflection coating. If we create that, you can see that on top of these pyramids, they are making small grains. It is shown over here. So small grains are formed. So we did the analysis and we showed that the reflection of this material of silicon is drastically reduced. So this is the specular reflection actually very much reduced, and we found that this does not affect our electrical property much. And this we already published in 2014. So if anybody wants, you can also go through this. So now I tell about the different low-dimensional structure. Actually, we know like in nanotubes already. I saw titanium dioxide nanotubes. Similarly, you can think of carbon nanotubes, silicon nanorods that we can be think of. So this is a one-dimensional structure. Two-dimensional structure is something like graphene or MOS2, like TMDC are the two-dimensional structure. You can also think of the that is TMDC, and that is so that is the phosphorine and the selenium. They are also like 2D materials. So now they are really lots of people actually working to play with this. But the main condition is what the important thing is that the density of states they are playing with, and density of state can be determined by how many electrons actually can bear by per unit energy levels. Okay, so total N is the total number of states available per unit volume. So if I go in different levels like a 1D, 2D, 3D, so you can see that how this density of states actually modifying, and finally in zero-dimensional case, that's a quantum dot case, it is a kind of delta function. That means that you can, if I show the density of states with respect to the energy, you can see that initially the three-dimensional cases it just followed kind of a simple parabolic nature, but then it will be a step function in case of 2D material, but then it will be a kind of delta function. So steps are they are like a sharp levels are forming. Keeping this in mind, actually, we can think of a free electron model. So how these levels actually form. So here actually we go beyond the group model, and where we consider if I have a small structure, small particle formation like quantum dot, you have a limited number of atoms existing. So in these dots, so how many states will be formed? So that we can easily consider the free electron gas model in a box model. So here, since the quantum dots, so we consider is in a cube structure, every edge having a length of L. So then the volume will be L cube. Okay. So if I now take the solution of this, then the boundary condition, because since we have volume, your potential within the box will be 0, then within this L length, your wave function will be existing. Beyond that, no, it will be an infinite barrier will be there. No wave function will be expected beyond the dots. So that means that you have the boundary conditions. So how many minutes I have? Do I have 15 minutes more?
So actually, we are 4 minutes.
4 minutes?
Yes, sir.
Okay. Okay. I tried to cuddle something. Okay. So I just step jump here. So you can see that if I take the solution, then solution is you can get as high equal to, this is a normalized form. So it is e to the power I k dot r. And if we take the dimension, so you can see the kx ky, because I already told about the reciprocal space. So you are not writing in terms of the L in the real dimension, then you are writing in the k space, then it's the nx, ny. So it means how many atoms actually involved in it. So different order can be finding out. So nx, ny, nz, 3 different directions. So different k levels can be obtained. And ultimately, you can get the eigenstate, energy eigenstate. So that also involves the kx, ky, and kz. So this is h cut square, kx square plus ky square, kz square by 2me. So that gives you the energy levels. And this is the discrete level actually can be formed within the boundary, in the dots. And then if you think of the dots, the bulk, you have a certain level. So generally the gray color actually shows the bulk levels. But in case of reducing dimension, you can see that your levels will be now quantized. They are separated out, and that means that it can absorb different amount of energy within the quantum dots. So utilizing this effect, people are making the LEDs. I also showed that this kind of material like a germanium quantum dot making within this normally the MOS structure, MOS structure, we can make the RAM we fabricated in 2003. And here, because since we have some limitations, because we cannot create certain number of dots, we cannot go beyond a certain number. So that's why people are now thinking of making some better productivity. So you can see that if I magnify these quantum dots, you can see that they are crystalline in nature, and you have lots of defects are staying within this. Now I showed that the kind of information I provided you, now how it can be utilized in understanding the different processes in real practice. So here you can see that in silicon nanocrystal, whenever we bombard this silicon ion oxide matrix, then you get the silicon nanocrystals, and utilizing this, we can also pump the erbium ions, and these erbium ions actually emit at 1.54 micrometer, which is the telecommunication wavelength. And we showed that by utilizing any costly laser, we can easily pump the erbium signal. And we can easily explain this one by it's called the energy transfer process. By knowing that in lifetime, we can easily see that how it can be populating the energy levels of the erbium ions, which can ultimately emitting at 1.5 nanometer. And whenever we replace this by germanium crystal, we can see that if I increase the germanium erbium concentration in the germanium crystals, then what we observe, we didn't find that kind of emission. We find instead germanium giving the better emission instead of the erbium emission. And when we analyzed in details is LED, is electrical property and these optical properties, and we find that if we feed this data by Fowler-Norden tunneling, it's electrically field-driven transition actually happening, and it can excite, hot electrons can excite the optical charge carriers, optical objects, and that's the RBM on the silicon nanocrystals. Then ultimately we can get the electron efficiency can be determined. So what is the emission we are getting over here? This electron emission signal we can see, and that can be
Professor Kanjilal.
Yes, give me 2 more minutes because
Hello. Okay.
Yes. So here actually I'm just connecting with the kind of information I provided in the beginning, how important they are in analyzing different types of experiments. Okay, experimental data. So here you can see that by knowing this structure, we can easily find out the electromination efficiency. Okay, so we can show that how the cross section actually improved by adding this part. So here's the lifetime. So lifetime having 2 different components, non-radiative and radiative part. So here I just step jump. So the response actually is made of 2 different components, radiative components and non-radiative components, and they are inversely proportional to the time lifetime and the population of the electrons. So if you go in details about this, then you can find out the quantum efficiency of those devices. So if you get a good electroluminescence from any device, use it for LEDs, you know that you should have a better quantum efficiency. So I just go in quickly and show that we are given a model. It's called the inverse energy transfer model. So which is also published in APL. So now, based on this ideology, actually, my group is now at the moment working different projects. You can see that composite material, memory devices, radiation dosimetry, surface and interface analysis, solar cells. So different structures we made. We make different kind of emission or different types of response we are getting. Utilizing that, we are getting the here actually you are showing that yesterday I can see that Professor Jing is talking about the AI. So basically the concept was based on the memory device, how this it will be storing the energy electrons in the matrix. So actually you are working in these details. So without going into details, I just show that in quickly. So this part actually here actually I showed that our group recently we published this one for making the RAM. As I showed previously, that germanium nanocrystal we can create within the MOS structure, but this is not the end of, because since they have their own dimensions, so we cannot scale further. So that's why we have to use without using any nanocrystals. So here actually we are utilizing the simple matrix. So how to utilize the matrix where the oxygen vacancy is actually controlled. And by controlling this one, we use the ion beam technique to control the vacancies. And by doing that, I just step jump. So I showed the vacancies are really formed, and that we confirmed by the experience result. So the structure was degraded, by still your efficiency is not going to degrade. And we create by ion beam, actually, we can create the nano channels, and these channels are really efficient enough to create the high quality RAM structure. And this is the structure actually the device we formed. And finally, you can show its efficiency, and you can see that how good quality devices we are making. These devices are now working within 0.5 volt. So it is a tremendous effort actually we are making here by utilizing the ion beam technique. We just control your operation potential of any device, which is normally it is 5 volt. Now
Yes,
we bring down to 0.5 volt.
Good afternoon.
Okay. So here
Bus, I'm attending my lecture.
Within 1 minute, I just.
Is there any emergency?
And here actually I just concluding what I said. I had given you in the beginning. I conclude in the beginning that the different steps involved in the semiconductor physics, and based on that, we showed that how the different structure can be formed, and different types of field we are dealing with in the laboratories, and where oxygen vacancies we use for controlling your RAM application. So with this, I would like to acknowledge my students in my lab, and also my collaborators in India and abroad. And also I would like to acknowledge the DST, BRNS, and the Civil University, and even the Humboldt Foundation, because I was a Humboldt Fellow. So I use the support from the Humboldt Foundation to develop my laboratories and to conduct all frontier applications in the laboratory scale, because I'm not focusing on that much in this scale, because since the students are basically involved in this school, so that's why I give more input in this the basic point of view rather than the application point of view. So with that, I'd like to thank, and I thank once again the organizer and Professor Emisa for giving the opportunity. This is my website. Details of my publication and my details about our group can be found this website. Okay. So I'll be happy now to take any questions.
Thank you, sir. Thank you very much. Sir,
So how can I see you? I cannot see.
sir, just a minute.
I'm here.
Yes, sir.
Actually, I can see the. I can see this. I cannot see the picture.
Kanjilal, thank you.
Yeah, so I'll be really happy now. If any questions, if you have any questions, you can ask me.
Okay, sir.
Is there any, Niklesh?
Yes, sir. There are questions.
Yeah, please.
First question is from Venkata Sai. Why different electron levels are combining in one single point? So this might be
which part actually you're talking about?
Sir, might be possible. Your slide, your starting slides, you showed some graphs now.
The band structure you're talking about?
Yes, sir. Yes, sir. Yes, sir.
Okay, let's go to the band structure then. So because what I choose to say about this, because I have seen that when I take the class, many people having the confusion about this. So that's why telling all big stuff is almost useless unless they are knowing these things. Okay, you are talking about this point, na?
Mm.
Am I right?
Venkata Sai. Sir, I'll unmute.
So you are talking about this point, where the gamma point you're talking about?
Venkata Sai, please confirm.
Yeah. Yes, sir.
Yes.
Yes, sir. He is talking about that point only.
Yes. So gamma point is the point from where actually we find the billion zone. Whenever I talk about the billion zone, you know that it is the reciprocal space. If you ever think about the reciprocal space, you have the dots. Okay. So and the center from where actually you are finding out the distance of different. Because if I take a, I should have a 1 billion zone here also. So better I go back to one of the structures so that you can see, because you need to get one structure. Because I think that, so this is your structure. Okay, so you can see that this is your one of the unit cell. This is
Yes, sir.
Mm.
So you can see that one of the unit cell actually is shown over here. This is the real space. But if I think in case of reciprocal space, then what actually you can think, the center, it will be giving like you have the gamma point, and then you have the Wigner's fixed zone. That means that you can get the diffraction spot, and in case in the middle of the two different points, if I take the vertical line, the bisecting these two different joining points, so then you can, if you can join them together, then you can get the a rectangular, a square shape of billion zone. So now if I draw a vertical line from this gamma point to the x-axis to the particle of this line, it's called the x point, that's the high symmetry point, then it is called the gamma to x point. Okay, in this way, how the electron, your energy distribution actually changing, the electron density of states actually changing. Similarly, if I have the box-like structure, then you have the corner to the gamma point. If I connect them, then it is, you are talking about the corner, means how the electron density of states actually changing in that direction. So whenever you are combining them together, every time actually you are actually starting from the gamma point. So at this gamma point, all states should overlap. So they are converging at that at this location. So because of that reason, actually, in this band diagram, basically the gamma point, all states they join each other, because this is the origin of this. And then you are going to the high symmetry points, X and the gamma L, or whatever points actually you have. It is only the point, this is source point from where actually you start finding out the K point, because K equal to 0. This is the K equal to 0 point.
Okay. Next one.
Next question is,
Niklesh.
sir, if we take many body problem, what type of computation we require for the Hamiltonian and wave equations?
Because actually I'm not a computer specialist, but actually I am collaborating with your theoretician. So what I learned that whenever you have a very complex atoms and you have many valence electron outside, okay, not only one electron, in that case it is not only the electron you are Here in this case, for simplicity, we are talking about the interaction between the atoms, atomic cloud from two different atoms. But in that case, it is not only the two different electrons from the two different atoms. At the same time, also you have the interaction between the electron-electron interaction within the atom. Because you have valence electron, you have the many electrons. Like silicon, you have seen that you have 4 electrons outside. So that means you cannot think about this only single atom, only electron contributing in the valence structure. So that's why it will be much more complicated. So then you take help of quantum computation, because Hamilton will be much more complicated in that case, because you not only have the 4 or 5 different components, you have much more different. Like I can show you that whatever I showed that time. So the
Okay.
so previously actually I showed you the different components, not Hamiltonian components.
Yes,
for
yes.
single
Yes,
electron.
yes.
So here actually you can see that in the previous slide actually it is shown over here. So you can see that it is not only giving only, this is for 1 electron from every atom, but now this Hamiltonian will not be that so simple. In that case, you have to have far more other components which are talking about the even the electrons which are lying within the valence band of an atom itself. Okay, so you have to also take care of this thing. So then that kind of thing should be handled by some computer program, not by simple analytical way.
Okay, sir.
Thank you. Next one.
The
Next one.
question is from Afnan. How the formation of heterojunctions between two semiconductors using compounds contain symmetric and antisymmetric molecules?
Antisymmetric molecules. We are talking about the state, not the molecules actually.
Okay.
This is the singlet state and the triplet state. And here actually that is the thing actually I wanted to clarify here, because this question I regularly get from different students in different levels. Actually, whenever you are talking about that, because you know the electrons are fermion, so because electrons fermion means they have the half spin is half, is not 1. So that means in this case, when you are talking about one state will be occupied by 2 electrons, then either because you know that from Pauli's exclusion principle that 2 electrons cannot take the same level of same electron spin. There must be opposite spin. But if you have to take the because since you are making a bonding or atomic bonding, you are making 2 atoms are now contributing, then electrons from 2 different atoms are contributing. Then if they are coming very close to each other, then this electron can also take the same level. In that case, there are 2 different conditions may exist, because for fermion it should be asymmetric. I know that quantum mechanically. So in that case, 2 things can be happen when your spins are asymmetric, but spatially they are symmetric. But if it is asymmetric in the spatial in nature, the spins can be symmetric. That means that 2 spins can be parallel, but they are symmetric in the space. But even if the electrons take the same state, both electrons come to the same state, since the Pauli's exclusion principle cannot allow to have the 2 parallel spin together, so it will be opposite. In that case, your function should be symmetric. So in space spatially, this should be symmetric. Okay. So 2 different
Thank you.
cases. That's why I
Thank you.
showed that when the spins cancel, they are anti-bonding. When spins are there, bonding, then when the spins are existing, it will be anti-bonding. So singlet
Thank you.
state, because you can see that mostly in the chemist, actually, the people who are working in the chemistry, they basically use the concept of the singlet state and triplet state. And sometimes they use the anti-bonding and bonding state. Sometimes people are confused that what is what. So that's why I'm telling you that what actually the main concept is coming from the wave function. When 2 electrons are overlapped, then how they can share and how 2 different contributions, spatial and the spin part, they contribute together to maintain the asymmetric condition.
Farhan.
That ultimately tells you the singlets and triplets set.
Okay.
Thank you.
Thank you.
Niklesh.
Sir, rest.
Niklesh?
Yes, sir.
We will send the rest of the questions to sir, but also Professor Raviji to thank you, our speaker.
Okay, sir. Vijay
Speakers, in fact.
in the meeting, sir.
Is he in the meeting?
Yes,
Okay.
sir. So for the
Unmute him.
Vijay, sir.
Professor Vijay. Kanjilal sir.
Yes.
Kanjilal sir.
Yes,
Hello. Yeah, I'm thankful. We are thankful to you, sir.
Yes, it's my pleasure.
Yeah.
I think that you understand my concept, because what I realized that because if you even I think whenever you're teaching in the class, you might have seen that though we may talk about many different applications like high-end applications, but if you do not have the basis clear, then the application part will be completely in dark.
You are right. You are right. You are right.
So that's
You are
the reason
right.
actually I thought that better I give the some kind of application at the end, rather, because anybody can read my paper, they can get the application. But best thing is that why I choose the material and why I choose that kind of understanding. So before that, I
Now,
want that to give
both
this.
of you cleared the basic things.
Yes. So that
Both
is
of you.
because
Both of you. Professor Singh also and you also. Very good. I have heard very good things about your university, Shiv Nadir University.
yes, please
I
visit
have
us
never
if
been to
you have
that
time.
place.
Over.
I have never been to that place.
Yes, you are welcome. So please let me know when things will be over. These things over. So I will
let
come in.
things stabilize. Let things stabilize. Let
Yes.
us see the God's mercy again. Things normalize, and then we'll
Yes,
invite you over here also.
we are really hoping so that
Yeah. We are eagerly waiting for His mercy, because
yes, that's true, because we are really waiting that when this thing day will come.
the mercy will come soon, sir. And then we are inviting you in advance to visit us in September also. We are organizing one mega conference on
Okay,
nanotechnology.
okay,
On
very good. Then
nanotechnology.
okay,
Yeah.
so then it will not be a school. Then I'll give some better explanation of our research here.
Yes.
So,
No, it's a very good research. You are tackling many aspects of your research. I have seen it.
Yeah, because actually I have six
Okay.
different PhD students now working, so they are working in different fields, and they are all utilizing the.
Okay.
Because here actually I'm playing with the basic concept in different fields.
Okay. Good.
I'll be very happy to
You have also PG.
visit
You
you
have
in
also
September.
PG program in physics also.
Nicholas, can you hear me now?
Kanjilal sir, you have
yeah,
PG program.
now we can hear you.
We have the BSc
Okay.
integrated BSc program, and we also have the PhD program here. MSc did not start till now,
Okay.
but we are going to open the MSc soon. Now
Okay.
we have the 4 years,
Professor Vijay will.
integrated
Yes.
BS program.
Okay. Thank you, sir. Thank you.
Okay,
Now,
So
welcome.
Vijay will take up.
so should I continue?
Yes, please.
Yeah.
Yeah, okay.
Over to you.
So, I would like to introduce our Professor Vijay for the vote of thanks. Professor Vijay is presently working as an assistant professor, Department of Physics, National Institute of Technology, Srinagar. He received his PhD in physics at the beginning of 2013 from SLIT, Longowal. From 2013 to 2015, he was a postdoctoral research fellow in Phosphor Research Group, Department of Physics, University of the Free State, South Africa. He has received the Young Scientist Award under the Fast Track scheme of the Department of Science and Technology, Ministry of Science and Technology, Government of India, New Delhi. He is currently engaged in research of functional materials, solid-state luminescent materials, ion beam analysis, biodegradable composites, smart polymers, and biomedical applications, with more than 80 research paper publications in international peer-reviewed journals, 10 peer-reviewed conference proceedings, 8 book chapters, and edited 4 books, authored and co-authored. Now I would request Professor Vijay Kumar to kindly extend a vote of thanks to both of our guests for their kind sessions.
Thank you, Nicholas. Our most valued invited speaker of the day, Professor M.A. Shah, organizer of the short-term course. Distinguished delegates, ladies and gentlemen. I deem it a great privilege to propose a vote of thanks on behalf of the Department of Physics. I would like to thank Professor Rajendra Singh and Professor Aloke Kanjilal on behalf of Department of Physics. Thank you, sir. Professor Rajendra Singh delivered a very wonderful talk on electrical analysis of materials and devices. Professor Singh explained in details the new concepts about the 4-pro method. We all have done the same experiments in our solid state lab, but that was a very basic. And he explained it in a very good manner. He also talked about how we can modify the samples with lithography and etching. It was really a very useful talk, especially for the students. The second talk by Professor Aloke Kanjilal was on fundamental and frontier applications of low-dimensional semiconductors. The way Professor Kanjilal talked about the semiconductors in lower dimension is commendable. I am sure that the students and also the faculty members will definitely have benefited from the information shared by both the speakers. Thanks again, sir. I once again express my heartfelt thanks to our invited speakers of the today's session. We are fortunate enough to be backed by the motivated and dedicated members of the organizing team. I am thankful to delegates and participants for sparing a valuable time from their busy schedule to be with us virtually. I thank you all for your attention. Thanks for joining. Thank you very much, and looking forward to see you all again tomorrow. Thank you very much.
Thank you.
Thank you, sir.
Thank you. Thank you, Vijay. Thank you, Vijay. Thank you, Vijay.
Thank you, sir.
Thank you.
Thank you.
Thank you.
Thank you, Professor Sir.
Thank you, Kanjilal. Thank you. I wish you someday very soon in person in Kashmir.
Definitely, I will visit you.
Yeah, please,
Also,
along with
you are
family.
equally welcome in our university. Whenever things will be fine, then I will also invite you. Please
Fine.
come visit us and see our facilities.
Yeah, I wanted to visit. I have heard many good things about Shiv Nadir University. I have heard many good things regarding implementation of new education policy, regarding some innovative things. And one of my, he's a well-wisher and a neighbor, Professor, this one, he was a vice chancellor of a university, Professor Sadiq Wahid. He's a visiting professor of your Shiv Nadir University.
Okay.
Yeah. He's a neighbor also. He was a vice chancellor over here in one of the university.
Okay.
He had been in US for a long time, but he told me that he's a visiting professor over there in Shiv Nadir University.
Okay. Because actually in our university, we have many different branches are there. It is not only the science, at the same time, engineering branches there, arts is there, arts and dramas are there.
Yeah.
So it's many different departments running in parallel. So sometimes actually whenever there's a get together, then we only get to know each other. Otherwise, mostly we are focused on our research and teaching part. Yes.
Separate. Anyway, thank you, sir.
Okay.
Niklesh,
Yes,
shall we take
Thank you very much.
Shall we take leave?
Yes, sir. Please.
Thank you.
Thank you, sir.
Thank you.
Okay.
Thank you.
Okay, bye.
Okay, sir. Okay. Vijay, thank you.